Okay, so now we can start?
Yes.
Okay, so I'm audible, I hope. So good morning, respected Principal Madam, Controller of Examination, Dean R&D, dignitaries, faculty and staff members. This is Dr. Nobamita Banerjee Roy, HOD Electrical of Neurological Technology. On behalf, I welcome you all to the inaugural session and day one of AICTE sponsored short-term training program on recent trends in Internet of Things and control of distributed generation. The topic encompasses multiple range of disciplines of engineering. It had been a hard task to gather resource persons from all over India, various sectors involving both academic institutions and industry. I would hope that this STP would be beneficial to all the participants. The session is being held in Google Meet platform and its live broadcast is going on in YouTube and the participants have joined there. Now I would request our principal madam, if her network is suitable, to say a few words.
Good morning, Dr. Nobamita Banerjee.
Hello, madam.
Yes, may I audible?
Follow, please unmute. Please unmute. Please mute. Follow, please mute.
May I audible?
Yes, madam, you're audible.
Yes. Good morning, Nobamita Banerjee.
Follow, please mute.
Dr. Abhinandan De, Professor Amlan Chakraborty, Professor S.C. Konar, and other dignitaries present here. All the participants. Without the participants, no events will get the success. The electrical department has taken the initiative to organize the staff development program on an emerging topic, the very good topic they have chosen, and that STTP is funded by AICTE. That is also a very major part, and I wish all the best of this 5 days staff development program. And as I seen, actually in the program, all the dignitaries, all the speakers are very renowned speakers. I am very much grateful to all the speakers. Today, Dr. Professor Abhinandan De is present, and on other days, other dignitaries will come. However, I am really very much grateful to all the dignitaries present here, and also I am very much grateful to the speakers who will be giving their experience, will be sharing their experience and will enlighten our faculty and staff members. And I believe all the faculty and staff members will be enlightened through their knowledge. Thank you, the electrical department, for organizing these nice STTP, which is very much beneficial for the students, for the faculty and staff also. Few students may attend, as I discussed with electrical HOD, maybe. And really, I will not take much time. Once again, I welcome, and I'm also grateful to Professor Abhinandan De, very good resource persons, very well-known professors in this field. So I will not take much time. Thank you, Dr. Ramonita, for giving me scope to say some words. Thank you, and I wish all the best of this staff development program. Thank you.
Madam, actually, Professor B. Das, who is the speaker of today's first session, she is also there, but she is muted.
What is the name, madam?
She is Professor Laila B. Das from NIT Calicut.
Oh, sorry. Actually, I have not seen. I seen Professor Abhinandan De. I have not seen. Very sorry, madam. Very much welcome.
Okay. I'm listening. I'll be
to you. I am very much grateful to you for giving your valuable, precious time for our faculty and staff members. Madam, once again, I am sorry to mention your name. Actually, I thought only one speaker is present here. Thank you, madam, for giving the time. Thank you.
It's fine. I will be speaking very soon. It's okay.
Yes.
Yeah.
Thank you, madam. I would now request our controller of examination to share a few words here. Sir, please. Professor Amlan Chakraborty is the controller of examination as well as the professor of electrical engineering department. I would request you to share a few words in this session.
Thank you very much, Professor Navamita Banerjee Rai. I am able to see an old acquaintance. I think Shujit বিশ্বাস is here. I can see his face. Thank you. Good to see you in the morning. And also, I welcome Dr. Avinandan De and also Dr. Laila B. Das, who has joined from a very remote place, NIT Calicut, and they're going through some weather disturbance these days. And I'm sure that she has joined with a lot of difficulty in managing the time. Anyway, thank you, Dr. Avinandan De, and thank you, Dr. Laila Vidas, and thank you also, Mr. Shankar Mukhopadhyay. He is also an old acquaintance. We welcome you all, also Dr. Sujit Vishwas, to this program, which is being inaugurated today. I am sure that with the current fast development of smart grid and very sophisticated technologies in smart meters, synchrophasers, numeric relays, I think these applications of IoT and embedded systems is going to take a big role in the formation of the future smart grid. I think all the faculties of our institute and other faculties who are going to participate in this program will immensely benefit from the very capable uh, faculty who is going to take the lectures during the next few days. Thank you all.
Thank you, sir. Professor De has already joined. Mr. Shankar Mukhopadhyay has also joined. Thank you, sir. And another expert, Professor T. Kishore Kumar from NIT Warangal. Welcome, sir. He has also joined with us. So I would request Professor De, Abhinandan De first, to share a few words for today's session and the program that we have started from today.
Yeah, good morning, Navamita. Thank you for introducing me.
Thank you.
So it's a great pleasure and a privilege for me to be invited in this short-term training program to be as a speaker. And I wish all the best for the 7 days long program. Now, it's a good initiative that during this pandemic situation, you are able to arrange such a lovely program, which I believe will be beneficial for all the participants. In fact, many institutes are probably not in a position to utilize the resources to the best of their abilities due to the lockdown and many other associated problems. But it's good to see that even in spite of having the physical difficulties, you have been able to organize the program online. And I wish all the success to the program. Right? And
thank you,
once
sir.
again, yeah, on my behalf, I express my gratitude to the organizers and all the resource persons. Thank you so much.
Thank you, sir, for such a nice words of encouragement.
Navamita,
Yes,
Navamita,
madam. Yes, madam.
in the line of Abhinandan sir, I would like to mention 2 lines that during the lockdown period, our institute has taken the initiative from 16th March to continue the teaching learning process in the online platform, and several webinars we have organized, and like you people, resource persons, they have delivered in different departments, like this type of programs we are conducting. Thank you, sir, for your best wishes.
Yes, thank you, madam. In fact, I know that you are pioneer. In fact, you have shown the way Long
that
time
is
back.
that is only true for the blessings and support from you, like people said. Without
Okay,
your
thank
support,
you.
without your blessings, this would not be possible. Today, all of you have given the time to us. You, Shankar Mukhopadhyay sir, NIT, from the NIT Calicut, several professors are there. Sujit Biswas sir is there. So you were giving the so much time to us, sir. Thank you.
Thank you.
Thank you, madam. Once again, I would request Mr. Shankar Mukhopadhyay. He is with us. Sir, please share a few words of encouragement.
Good morning to all of you. It's really nice to see that such an excellent program is going to be organized by your institution. Why it is nice? Because today, in fact, although despite the pandemic situation, you are very sincerely trying to organize a program which is very pertinent for today and tomorrow's entire technological society. As we are talking about IoT and embedded system, and I belong to power sector, right now without these systems, the sector cannot move. And all you know that power is the one of the key driving resources of modernization of the society, and the growth of the society is indicated with the usage of electricity. So I hope such program will be very useful to all the participants. And at the outset, I also express my deep gratitude to you for inviting me in the inaugural session, and I convey my respect to all other senior members who were here in the inaugural ceremony. I am not individually mentioning anybody's name because everyone to me is very vital and important for this particular discipline. But uh, last but not the least, I should talk about Navamita's enthusiasm and Dr. Kanjilal's patronage, for which these are possible. Thank you. Wish you all the best. Thank you.
Thank you, sir. Thank you. May I now request Professor Kishore Kumar, T. Kishore? He has joined with us from NIT Warangal. He is one of the speaker of our program. Sir, am I audible to you, sir? Would you like to share a few words with us?
Yes, madam.
Good
Is it
morning,
audible,
sir.
madam?
Good morning. Yes, you are audible.
So, at the outset, I would like to thank the organizers of NIT Calcutta for inviting me to be participate in this inaugural program of this 2 week AICT program. During this particular current pandemic system, it's very apt, and you people are taking a risk to conduct this particular program on online. And coming to the program, the IoT and embedded systems, as our Honorable Prime Minister vision, Digital India. So there are a lot of programs that AICT brought to give awareness to all the faculty to upgrade their professional growth, like IoT, 3D printing, cloud computing, blockchain, machine learning, artificial intelligence. So definitely these the cutting edge technologies are very much useful to upgrade our knowledge and to apply for the real time applications. And that too very apt that you people have taken a particular application, smart grid power distribution, and how you can use this particular embedded systems and IoT for that particular application. So it's very nice idea. I'd like to appreciate in particular head of the department, madam. Of course, this is my first time I visited IIT Kharagpur and another institute along with Professor Das. But this is another good opportunity to share my knowledge and have the relationship with your institute. In future, definitely NIT Warangal is ready to have a joint collaboration with your institute to organize such programs. So we are also having electronic and ICT program. In that also, in future we can conduct such type of programs. Definitely, we are with you, madam. And once again, I'll appreciate and all the best for the success of this particular program. Thank you very much. Thank
Thank
you,
you,
madam.
sir. Thank you, sir, for extending your support for future programs. And thank you, sir, that you have given us the opportunity to collaborate with you in future programs. So, with all your support and encouraging words, I would now like to go ahead and I would like to say a few words of the first speaker of our today's session, Professor Laila B. Das. She is presently the associate professor in the Department of Electronics Engineering, NIT Calicut. She has a diverse mix of industrial teaching and research experience spanning about 30 years. As a young graduate specializing in electronics and communications from the College of Engineering, Trivandrum, Professor Das joined Kelton Controls as deputy engineer in 1981. She joined NIT Calicut, the erstwhile Regional Engineering College Calicut, as a lecturer in 1985 and proceeded to complete her master's in digital communications from the same college. Keen to actively seek and impart knowledge, Professor Das currently teaches courses on microprocessors, microcontrollers, digital system using VHDL, system design using embedded processors, artificial intelligence, and data structure at the undergraduate as well as postgraduate level. She has presented research papers in conferences of national and international stature and has worked on numerous projects. She has also participated in numerous tutorials and workshops conducted by the IIT and IISc. She was an invited member for Intel's workshops in the USA and Taiwan. Her passion is writing books, and her books have been published by Pearson Education and Cengage. They are readily available in Amazon, and a few of her noted books are on embedded systems, microprocessors, and multi-core systems. 8086 microprocessors to Pentium, multi-cores, Atom, and the 8051 microcontroller, architecture, programming, and interfacing, embedded systems, and integrated approach. Well, you can find more details about her in the website of NIT Calicut. So, with these words, and without wasting my time further, I would request Professor Das to start the session. Madam,
Yeah. Good morning,
your
everyone.
request. Good morning,
Okay.
madam.
Let me. Can you see my slides? No.
Not yet, madam.
Yeah.
You please go to present now.
Yeah. Let me. Can you see my slides? Are my slides visible?
No, no, madam, not yet.
Very
Madam,
good.
have you clicked present now in the Google Meet platform?
Yeah. I'm just going. I went there. Okay. Present now. Wait. Where does it come? Yeah. Present now is there. I can see.
Yeah. Then present now, madam, you need to select the window window or screen where your PPT is there.
Okay. A window. I have to take a window and show this. Can you see?
It's coming, madam.
Yeah.
Yes, madam. Now it is
Right.
visible.
Okay. It's fine. Everything is fine. Can you hear me?
Yes, madam.
So, shall I start my presentation?
Yes, madam, please.
So, good morning, Calcutta. This is my first online presentation because all these days I was a bit reluctant to accept any invitation for online presentations because till now I have been used to in-person presentations, and that used to be very good because I can interact freely with the audience. Now, the problem is that my interaction with the audience is not that much. I mean, I can't talk with see the audience. That's the one problem. But anyway, I think I'll go ahead with this. I hope I'm audible still and you can see my slides. Okay, fine.
Yes,
Hello?
madam.
Yes, ma'am. Okay.
Hello. Yes,
Yeah,
madam.
everything's fine. Shall I start?
Yes, madam. Please start. You're
Okay.
quite clearly audible and the slides are also visible. Okay,
Okay.
madam? Yes.
Okay, I'm from Calicut, and many people think I'm from Bengal because my name is Laila Bidas. Many people ask me, are you a Bengali?" But actually, I'm from Kerala itself. I've been in this NIT from 1985. My areas of interest are embedded systems and microcontrollers and microprocessors. But recently, I have started learning and teaching machine learning, artificial intelligence, and of course, IoT is a part of embedded systems. So I've been taking many workshops on IoT, hardware systems, etc. Mostly my work has been in hardware and in machine learning. Of course, there are a lot of options for it in hardware. That's what I want to discuss today. So my topic is embedded systems, machine learning, and IoT, putting it all together. So I'll be including some information, some fundamentals of all these things. I'll start with the fundamentals of embedded systems. So what I'm assuming is that not everyone is very clear about embedded system, in the sense that there are a few beginners, there may be a few experts, but still I should start on a beginning note about what is an embedded system. So I'll start as with an introduction. Some half an hour I'll spend on embedded systems, what it means, what you need for it, etc. So the first question is, what is an embedded system? So that means I should define what an embedded system is. So, by definition, an embedded system is one that is meant for certain specific functions. The word specific is very important. In the first earliest definition of embedded systems, the definition was it is a system meant for one specific function. But over the period of time, that one has changed to many specific functions. So, an embedded system is a system meant for certain specific functions. And usually, whenever we talk about an embedded system, we mean a system built on electronics. Now, specific function, the word specific function is very important, as I told you. So, because of that, the general purpose PC, even though it's 100% electronics system, it is not included in the set of embedded systems. And it is considered as a general purpose system. The PC is always a general purpose system. It's not an embedded system. But if you look around you, everything other than the PC, I mean, every electronic system other than a PC is usually considered as an embedded system. So your general purpose systems are PCs, desktops, laptops, etc. And special purpose systems are systems which are dedicated, like a camera, a printer, a scanner. All these things are dedicated systems for certain specific applications. And so they are included in the set of embedded systems. And also, say, look at it. The most commonly used embedded system is a mobile phone. A mobile phone is a very important embedded system. And embedded systems can also be part of a bigger system, like a washing machine. So we have some embedded electronics in it. So that is called that part that controls the washing machine. That is the embedded system corresponding to your washing machine. Now, if you look at embedded systems, the word for embedded systems is it is ubiquitous. Ubiquitous means it is found everywhere. So if you look around, you can see in your house, you can see many embedded systems. If you have a car, there are a lot of embedded electronics inside it. And you have a washing machine, you have your AC, we have all these things, we have AC. All these things are considered to be embedded systems. And the general purpose system, you may be having only one PC, but you may be having a number of embedded systems within your reach. So the electronics included in automobiles, factories, aeroplanes, defense system, everything is considered to be embedded systems. So what does an embedded system have as its components? It has computer hardware, it has software, it can have mechanical aspects. A washing machine will have motors and mechanical movement, etc. There will be other technical components, and all of them together, they are designed to perform a few dedicated functions. And the last line in the slide is many of them need to meet real time computing requirements. Many of them implies not everyone. So, for example, if a mobile phone for some applications, real time requirement is not there. But suppose you consider a car, an automobile, it has what is called an anti lock braking system. That's a very critical function. So it has to meet real time requirements. Real time means this system will work with a deadline. So you want the brakes to be correctly applied within a certain amount of time. And if that time is not met, the deadline is not met, you consider the system, okay, it's a failure. So real time requirements is important. Deadline meeting deadlines is important for many applications. Now, just to give an idea of the application domain of embedded systems, you look around you, consumer electronics. So, consumer electronics means basically if you have a smart TV, that is one TV. That's one example of an embedded system, consumer electronics. If you look at household appliances like your washing machine, your microwave oven, they are part of this class. Home security systems, then automobiles. So in the automobile, you have engine control, you have fuel system control, door control, and many other controls, your infotainment. Everything is considered as an embedded system. And think of medical equipments. All your medical equipments are considered as embedded systems. Then see the one that you have, for example, blood pressure monitor, blood sugar monitor, they are all embedded systems. And you look at banking, an ATM system. See, all these are examples of embedded systems. And so that's why we say embedded systems are ubiquitous. They are present all around us, everywhere. So the next slide will give you some pictures. So these pictures are actually not necessary because once we talk about embedded systems, we know everything is part of this embedded class. You have a camera, you have aeroplanes, you have a toy, you have a car, you have an electronic tablet, you have your robotics. All these are what we're talking about, again, embedded systems. Okay, so what do we have in all of them? We have electronics, we have software, we have some mechanical parts. So we have what's called a user interface. We'll talk about it. So look at it, look at this list. Like embedded system as an all encompassing system of knowledge. So if you want to design an embedded system, actually, if you look at this, you might need teamwork, because this set of knowledge skills, every one person cannot possess all this knowledge. So you need some mechanical knowledge. You need to know electronics hardware. Software is absolutely necessary. Data structures. Data structure simply means that you'll be dealing with data. Sometimes you have large amounts of data. Aeroplane will be generating large amounts of data. So how to handle this data? To handle that, we need to know data structures. Then networking simply means you'll be having connectivity to some network, for example, internet. So how to handle this internet, how to deal with this internet technology, we should know networking. Signal processing is known to all electronic engineers. Why signal processing is necessary is because the signals that we use may be image, will be your audio, will be a image, your video. So we can't use them raw. We have to do some processing on it. So for that, a knowledge of signal processing is required. Then why social awareness? Social awareness required because what's the use of all this technology? Where do we use it? And if you want to have a new design, why do we need it? So we should have social awareness of it. Now, because of this COVID situation, lots of people are designing so many systems for sanitizing and for various other things related to this particular aspect of social problem now. Okay. Now, what is very important? The next thing that is very important for any electronic system is called the user interface design. User interface design simply means that how the user will use your design. If you take a mobile phone, look at a mobile phone, and if its user interface is bad, you will not like to buy it. So just look at when you're typing it, if the font is not good, the way the different apps are presented. If that user interface is not good, you wouldn't like to buy that mobile phone or use that app. So user interface design is very important for any electronic device, for any embedded system. So a person who's designing it should have some knowledge of user interface design, or he should find a special or expert in user interface design who will present a very good user interface to the user. And finally, we need electrical knowledge. Electrical knowledge is required because power system design is very very much important. So electrical system knowledge is required, and basically because we need power awareness. Power awareness simply means that you should have a knowledge of how to reduce power, because we would like to have devices which are of low power dissipation. So now look at the slide. It says that what are the figures of merit for a typical embedded system? For example, a portable device. Suppose you have a handheld device, then the figures of merit. What are things you would take note of? First of all, you would like to have low power dissipation, because this particular system may be operating with battery. So make sure that a design is of low power. Then if it is small physical size, we would like your hardware to have a very small physical size. Take the case of, suppose you want to monitor the animals in the forest. What you would do is you would have a physical board, an embedded system board, and you will clip it to one of the ears of an animal. So you can't have a very large board. That board should be very small. That small board, very tiny board, should be uh, put on the ear of an animal. So that small physical size is important, basically because of the application. Then the code size, there will be software. So the code size should be small. Why? Why should be small? Because usually when we have a hardware, you will be having a microprocessor, microcontroller. In that microcontroller, you would have your ROM. All your code is going to go into that particular ROM. So unless the code is very small, you can't fit it into that particular ROM size. The ROM size may be limited. It is not as big as what you have in a PC. So because of that, your code size should be very small. Essentially, it should be as small as possible. Then, of course, we would like it to perform well. So we say it needs high speed of response. The speed of response of your system should be good. Then the system, a portable device, will have should have these figures of merit. Now, that is for a portable device. All these things may not apply to every embedded system. For example, if you are going to do embedded electronics in a factory automation, then the small physical size is not important. For a defense application, your small physical size is not important. So it depends on the application. Some applications, and of course, if you're doing what's called factory automation, you don't have to bother about user interface directly for that particular embedded part. Okay, so it depends on the application. From case to case, we should decide what are the figures of merit for that particular embedded system. So previously, I just mentioned that a PC is not considered as an embedded system, but a smartphone or a mobile phone which is smart is considered as an embedded system. So sometimes we have a doubt. The smartphone is also performing applications similar to a PC. We can do some sort of software application. We have a lot of apps. So many things that we do on PC nowadays people are doing on the smartphone. But there's a basic difference in the design of a PC and the design of a smartphone. What is the basic difference? So the design of a PC is easier because the constraints are less. Constraints means you don't have to limit it to certain things. For example, for smartphone, you have to make sure that it has a small size, its power dissipation should be small, the code size should be small. All this we should take into consideration very much for a smartphone. For a PC, also these may be important, but it's not as limited as in the case of a smartphone. So the design of a PC does not have this many constraints, but the design of a smartphone has a lot of constraints. So that way, the smartphone design is very critical. PC design is a bit more easy. Even then, the dividing line is becoming a bit fainter because currently, when we design a PC, so the PC simply doesn't mean a desktop, it can be a laptop. And we want laptops which are having very low power dissipation. We want it to have lightweight, we want it to have a small physical size. So that way, the dividing line between the design of a smartphone and the PC is becoming fainter, but still, in the current scenario, the smartphone design is more critical than the design of a PC. So as things stand still, the PC is still not considered as an embedded system because it does not have that condition of specific functions. It has many general purpose functions. Now, So, what are the, again, once again, just to make it clear, the features of a typical embedded system are it has a small set of functions, it should have low power dissipation, has limited memory and limited number of peripherals. And applications are not alterable by the user. I'm not talking about the software apps. So once you have a mobile phone and it has a certain number of peripherals, you're not going to, you will not be able to add more peripherals because it's already decided. And if you are doing an embedded system, like as I told you, monitoring the animals in a forest, monitoring the trees in a forest, once you set it up, you're not going to be able to change the application in the hardware level. It's already fixed. You design it and keep it as it is. And again, the next, what is many embedded systems are not accessible directly. Simply means that suppose you put it in a forest, suppose you put it in an area of dangerous areas like mines, etc. We cannot access it directly. So they can be anywhere where we can't access it. Suppose a problem comes, we cannot solve the problem. If you have a problem with the PC, we simply have use the keys control all, delete it, resets, and therefore things can be set right by the human being. But many embedded systems are not accessible, so they should be able to monitor themselves. They should be self-correcting. They should automatically reset and do their corrections themselves. There is no human intervention to correct the problems of an embedded system when it happens. So that way, the designs also should be very, very carefully done. And all the hardware, like your microcontrollers, will have special methods by which, if the system runs into an infinite loop, you can reset it. Automatically, it gets reset and gets started easily once again. So it has to be a very self-sustaining system, embedded systems. And of course, it has to be highly reliable. That is not specifically of an embedded system. Any system, we would like it to be highly reliable. But sometimes, when we have some critical applications, like suppose you take a mobile phone and go to the railway station with your ticket in it, and suppose it doesn't work, you're stuck in the railway station without a ticket. So, as such, we consider applications where reliability is a very great issue. And as I told you, it needs to operate with time constraints. Like, for example, if an application for defense, we can't afford to miss deadlines. So time constraints are very, very important for a typical embedded system. So what are things we have in an embedded system? We have hardware and software. The main components are hardware and software. And partitioning of these two dictates the qualities of the system. For example, what this means is, suppose I have an image processing to be done. I can do it in hardware. I can have a hardware for doing image processing, or I can use software for image processing. Suppose you want to do image compression. Do I want to do in hardware? Do I want to do in software? If I do it in hardware, the possibility is that it will be fast. The image processing will be fast. If I do it in software, it will be slower. So, which do you want? Suppose you make in hardware, you get a faster system, but probably your price will be more because you have to have a hardware chip. So that way, how good is your system? That is decided by how well you partition between the hardware applications and the software applications. So as far as possible, if you can put everything to hardware, is fine, but then system will become expensive. It may generate more power. All these problems are there, but you have to have a trade-off between cost, power dissipation, and speed. All these things should be done at the design level. So, as I told you, finally, the important concerns for its consumer items will be reliability, connectivity. Connectivity is very, very important now. Connectivity means if you have a device, do you want it to be connected to any internet network? The most important network that we are all familiar with is the internet, your World Wide Web. So previously, suppose you had a camera. After taking photos, you would take it to your laptop or your computer, use a USB cable, and download all your pictures to your computer. But now nobody likes it that way. As soon as your camera has clicked a few photographs, probably you would like to send it to some location. You would like to send it over a communication system. So if your camera has a Wi-Fi capability or Ethernet capability, you will be very happy. So connectivity is very important currently for any embedded device. And of course, as I told you, good user interface is there. necessary. It should look good, and it will be easy. It should be easy for the person to handle that device. And security is very, very important these days, because you hear of so many things being hacked, your data is being taken by many, many people. So security, your system should be very, very secure. Software security is very important. These things should be taken into consideration. Now, a question that I used to ask people when they go for a talk on embedded systems, when I have an audience, the question was, what are the three P's to be taken into consideration for ES design? Three P's means three words starting with P. So since I don't have an audience to answer it, I'm answering it myself. The answers are, the three P's are performance, power, and price. And you know that performance should be good. That means speed should be high, power dissipation should be low, price should be low. So when designing a consumer item, these three P's should be taken into consideration and ensured to be good. So finally, the components of an electronic product will be hardware, software, networking, user interface, and packaging. Packaging is very important. As you know, it should be packaged well. Then only it will sell. Now, the general model of an embedded system. See the general model of an embedded system. An embedded system generally has, what you say is, it has sensors and it has actuators. So that means data, information should be taken from the environment, from the physical world through the sensors. Then there will be a microprocessor, or we say a microcontroller. A processing system should be there, and this processing system will have connected to it a memory. And then there are actuators. That is, depending on what information is given by sensors, the actuators will perform function. For example, I'll give you a simple example, simplest possible example. Suppose it's a temperature monitoring system. Temperature monitoring system, to monitor temperature at various locations, you connect a number of sensors. And these sensors will sense the temperature and give the data to the processor. You can give the data to the memory, and inside the processor, some calculations can be done. And one calculation possible is you check whether this is higher than the set point. You give a set point. Suppose it is the detected temperature is higher than the set point, immediately an alarm should go, and a running display, something like that. All that is called actuation. So the actuation could be an alarm, the actuation could be a display. So these are examples of sensors and actuators. Sensor is one that senses from the environment. Actuator is something that gives out some result, actuations. Okay, and we have memory. This will be a general model of an embedded system. Now, when you say processor and memory? So practically what you'll do is, when you're designing a system, you will have a development board. So you will use a development. This figure shows a typical development board. This is a processor here. You have a processor here. And this processor will have a number of peripherals connected around it. And this is called a development board. And this development board, when you're developing it, it will be connected to a PC. Your software will be tested by the PC, and it will be burned into the ROM of this hardware. Hardware means your processor. And then once the design is over, you will take this processor in which all your applications, your code is there, and put it in a very smaller board and put it into your application. So this is a bigger board which is used for development, and you will be having a number of interfaces. You'll be having USB interface. You can have many other interfaces for this particular board. This is the development board. But finally, when you design it, your design board will be very small. You will take a processor and only the necessary sensors and actuators required. That will be there in your actual board. Just a minute. So when you are choosing your hardware development board, which board will you choose? That depends on various things. Which processor you want, and what's the speed, what is frequency. All these things will be taken into consideration when you're choosing a hardware. Okay, now in between, I'm just taking a difference between a PC processor and embedded processor. The processor that we use here is called an embedded processor. The processor that we use in a PC is called a general purpose processor. In a PC processor, what we have is the PC processors will be computationally very high. Computation power is very high. Suppose you take this PC from the laptop that I'm using now. The computational power of this this processor will be very good. But if I take the processor for my mobile phone, it is good enough, but it's not as high end as that in this PC. Okay, and the power should be low for an embedded processor. The power that this PC processor generates will be relatively high. Size is small for an embedded processor. Sizes can be larger for a PC processor. Similarly, power also. Now, in this context, because we're talking about embedded system, we have a term called thermal design power. Thermal design power means how much power this processor or any system will dissipate when it is running. The word thermal is used here because this is by definition, we are assuming that when some power is dissipated, there is a cooling system which will dissipate this power. Okay, which will dissipate this heat. So that's why the word thermal design power, thermal is used here. The word uh, term thermal design power expressed in watts is a power rating for a processor or a system. It does not represent the maximum wattage, but it indicates how much power would be drawn when running applications for which it is designed. So there's a TDP for every system. So I'm just showing you the TDP rating for various systems for you to get an idea of this whole thing. So you can just see that for for a smartphone, it is around 45 watts. For a very small old phones like your feature phone, it will be less than 5 watts. For your ordinary tab, it will be less than 12 watts. 12 watts. And for a notebook, that is your low power laptops, it will be in the range of 10 to 15 watts. And for high end desktop, it will be in the range of 130 watts. This will be a typical TDP rating. So if you want to have any system for which the TDP rating is small, the processor should generate low power. Then all the displays, the sensors, actuators, everything should be low power dissipating. Then only your system will be able to be a low power system. Now, another issue related to power is whenever we talk about performance, we don't talk about performance by itself. Previously, we say a system has high performance when when it is operating very fast. But currently, the method of talking about performance is the word used is performance per watt. So it is for 1 watt of your generation of power. What is the performance? That is, you should work fast, even for smallest wattage. When it works fast, it should not generate a lot of power. That is a requirement of your system. The system should have a high performance per watt, not simply high performance. And now coming finally to a reasonably useful embedded system, what it will have is it will have processors and memory. You have a processor, it can have memory. Sometimes the processor is not a single processor, it's a multi-core processor. For example, for your mobile phone, you'll have your main processor, then you'll have a DSP processor. Then this processor itself will be a multi-core processor. They can have a special process for audio, for image, etc. All these things. So multiple processors can be there and can be memory is there. Memory can be of different types. You'll have ROM, you'll have RAM, you'll be having different types of ROM. All these things are part of your embedded system. The sensors that you have are called MEMS. MEMS is a small microelectrical systems that we have. The small accelerometers, small gyroscopes, all these are small. And the actuators are also MEMS, that is your motors. All these are considered as MEMS actuators. Then all embedded system usually now currently have an operating system. So if you have a phone, you have an Android, you have an iOS, can have any type of OS. Even your tab will have some OS. And do you know that your ATM has an OS, your printer has an OS, your camera has an OS? So maybe the OS is not directly usable by or seen by the user, but there is an OS inside it. Usually it's called a real-time OS. And then can have a communication network. You will be connected to internet, or you can be connected to some other system. Then you will be having what's called a user interface. This is what a reasonably useful embedded system will be. Now, the most important part of an embedded system is the processing element. The processing element is your microcontroller. Sometimes you call it as an embedded processor. Sometimes you call it a microcontroller unit. Sometimes you call it an SoC, system on chip. All these are same. Basically, they are all the processing parts used in an embedded system. And some of the popular microcontrollers are, you would have heard all these popular microcontrollers. Some of them, 8051 is a very popular one, but it's a low end microcontroller. PIC is low, it's not low end. You have 8-bit, 32-bit, 64-bit PIC is available. AVR is a series which is generally used in robotics. Then you have a very important, currently very popular microcontroller called ARM. We'll talk a bit more about ARM. Then you have something called MSP430. It's a very low power microcontroller from Texas Instruments. This is very important because for medical applications, we would like the power dissipation to be in the range of nanowatts and microwatts. So such microcontrollers, which are low power dissipating, are very important. So this MSP430 is one such microcontroller. The high-end microcontrollers, high-end processors, all of you will know the difference between a microcontroller and a microprocessor. A microprocessor does not have peripherals inside it. Microcontroller will have all the peripherals inside the chip. It's a single chip computer. So I'm not talking about the difference between microprocessor and microcontroller. But when I say the microprocessor, I simply mean the processing element. So I mean the microcontroller itself, where the peripherals are inside it. Because for any embedded applications, we'll be using a microcontroller, which is also called a embedded processor or as SoC, etc. Previously, all your microcontrollers had 8-bit data, then it shifted to 16-bit data, then to 32-bit data, and now it's all in the range of 64-bit. The high-end microcontrollers have data bus width of 64-bit. That is the current state of the art. Now, again, a question which I could ask the audience is, which is the microcontroller which is used in a mobile phone? So most people would not have bothered to check, even if they are electronics people or computer science people. Still, most people would have just looked in the, let's say, the brand of the phone. They would not look at which is the microcontroller that is used. Even if they ask, most of them, the answers, it would be a Snapdragon microcontroller, a Samsung microcontroller, NVIDIA microcontroller. But actually, all these belong to a class of microcontrollers or processors, which is called the ARM. ARM, the ARM processor. It is called the ARM processor. Even a Snapdragon, all the microprocessors used, microcontrollers used in a phone belong to the category called the ARM processor. This is a very important processor in the sense that all the high-end applications currently are running on the ARM processor. If you look anywhere, yeah, except for very few other microcontrollers used for consumer applications, the ARM processor is the most popular one. And the ARM processor, we don't realize that it's an ARM processor because of the business model of ARM. I'm just going to talk about the business model of ARM to understand why we don't know much about the ARM processor unless a person has specifically learned about the ARM processor. It's not publicly known. So the ARM short history is that it's an ARMful. It means advanced risk machine. Risk, it stands for reduced instruction set computer. It was designed in the year 1980, the 1980s, by a company called Econ Risk Machine, and it is a risk machine. Risk machine. It is reduced instruction set processor in comparison to what is called a CISC. CISC is complex instruction set computer. In the 1980s, Motorola and Intel were the leading giants for making silicon. Okay, and they had some processors. But when this ARM was designed, it was found that ARM had less number of transistors and uh, less power compared to these process which are generated or designed by Intel and Motorola. So it became a runaway hit because it is very powerful and is also generated much less power. So because of that, what happened is that ARM7 became a very popular microcontroller. ARM7 at that time all the installations using ARM was done on ARM7. ARM7 was the most widely used microcontroller at that time. After ARM7, this company designed ARM9, ARM10, ARM11, etc. After ARM11, they stopped that series and started a new series with the same basic ideas called Cortex. Now, if you look everywhere, the process will be designated as Cortex A, Cortex R, Cortex M, etc. If you look closely at your mobile phone processor specifications, you will find it is having some number, Cortex A, with a number with it. That's a version number. Okay. Now, talking about the business model of RAM. Why is it that we don't know that ARM is the processor in a mobile phone? The reason is ARM's business model is different from that of Intel. So if you take your Intel, if you look at your computer, a branded computer, probably if the Intel chip is inside it, they would write Intel inside. What it is, what happens in Intel is that they design the chip, they fabricate it, and they sell it. So Intel has its own fabrication unit. They design the ARM chip, they fabricate it, and they sell it. That is ARM's. That is Intel's model. Then AMD also does the same thing. But ARM, the processor, what it does is in the beginning itself, it decided that ARM would supply only the design. They would not fabricate it. So what they do is they take the design in the form of a netlist or as a hardware description language file or as a transistor layout, and then they would sell it to licensees. For example, Samsung would be a licensee, and Samsung would buy it with billions of dollars, of course, would buy the design, and then this licensee, for example, Samsung or Texas Instruments, they would do the chip fabrication. The whole chip will be designed by them. Only the design, the inside core will be the ARM design. So ARM does not supply the silicon. So that's why. And then when Samsung gets this design and do the chip fabrication, Samsung will call it its own chip. So it will be like this. Suppose a licensee develops a ARM chip. This ARM core alone will be developed by ARM. Everything else, all these things, these parts will be designed by the licensee, and the chip will be designed by the licensee. So we have licensees like Texas Instruments, Infineon, Cypress, etc. All of them have bought the ARM design and then made their own chips. Okay, so a mobile phone is also an ARM processor, but of course the chip has been fabricated by some other licensee.
আমি ভুলে গেছি তারপরে তুমি বলার
Excuse me, madam. Sorry for the interruption, madam. Sorry for Deepu, madam. Please mute. Hello, Deepu, madam. Please mute.
আমাকে মিউট করা নেই, দাঁড়াও দাঁড়াও।
Please mute.
Okay.
Sorry for the interruption, madam.
Okay. Shall I continue?
Yes, madam.
Okay. Cortex is the new ARM series. There are 3 different versions of Cortex. One is Cortex A. Cortex A it's used for advanced applications. So if you look at your ARM mobile phones, Cortex A is used in mobile phones as well as in electronic tablets. And it is called an advanced version of ARM. And the most important feature about it is such an advanced chip can support an advanced operating system in it. That's why mobile phones can support Android and iOS, which are advanced operating systems. So that is a characteristic of advanced type of one particular type of design. And for any operating system to be supported, the hardware support should be there. Okay, that's why your Cortex A has to be able to support advanced operating systems to be stored inside it. Then we have something called Cortex R. This is generally used for factory automation and such things, where real time means things should work with the deadline. Any applications there within that stipulated deadline, the result should be given. So this particular series for real time application. Then you have a very general type of ARM, which is called Cortex M. Cortex M is simply a microcontroller. You can use it for any application. So whenever we are doing some design in academics like student projects, we usually take uh, Cortex M. We usually take Cortex M because Cortex M is used for general applications. Okay, and Cortex M general application also we can use it for many versions. There are Cortex M0, M1, M2, M3, etc., M7. So M0 will be a low-end microcontroller, M7 will be a high-end microcontroller. Now all these microcontrollers are manufactured by various companies, and therefore we'll get different boards from various companies. So if we take a particular board called LPC 2148, it is an old type of ARM. It is ARM 7. It is manufactured by Philips. So we don't know anything about this. We don't think about it as ARM, but still it is ARM. It is called LPC 2148. Now, if you look at some Cortex boards, Cortex M boards, Texas Instruments has a board called TIVA. Freescale has a board called FRDM. ST Microelectronics has boards which is STM series. Then you have boards from Infineon, you have boards from Cypress, you have boards from NVIDIA. All of them will be using the ARM based architecture. ARM core architecture is used by them, but they give their own names to the boards. Now, what about Intel and AMD? They are also very great silicon manufacturers. They don't manufacture ARM, they don't manufacture embedded processors. Intel and AMD design and fabricate processors for PCs and servers. But actually, Intel wanted to enter the embedded market, and for that, they decided to use their own x86 boards. They used it for a long time. They used Intel Atom, then they had Galileo board, then various other boards they had. But over the period of time, they realized that their boards weren't as low power as ARM boards. So now what Intel has done is it has given up its own boards, or its own process of embedded, and now they're using ARM itself for their embedded products. If you have heard about Intel Atom is one embedded processor of Intel. They tried to use it for mobile phones, but then it wasn't successful because it was generating too much of power. So they withdraw it, and now you find Intel Atom in some netbooks and some tablets. But still, the embedded market is almost fully with ARM. Okay, embedded market, the high-end embedded market is fully with the ARM processor. Now, along with this, I'm talking about Arduino. Have you heard of Arduino? Many people have heard of Arduino. If you look at some student doing some hardware project, they would have bought an Arduino board and run their project on it, and it be working very well. Now, what is so great about Arduino? Arduino is an open source prototyping platform based on easy to use hardware and software. So Arduino boards, if you look, there's a standard hardware on it and a standard software. Software is in the form of some functions. So if you want to have a generate a square wave, you simply give delay, some function name is given. If you want to turn on an LED on, some function is given. If you want to make an LCD blink, then also what will happen is you just have to give function. That is, the Arduino boards have been made in such a way that the user does not have to know about the hardware or software inside. The user can be totally ignorant about the inbuilt hardware and software. So what's the use of such Arduino boards? We would not like to teach electronic students using Arduino because we want them to learn hardware and software. But if a student of mechanical department wants to do some electronic project, he can take an Arduino board and he can very easily do a project. He does not have to know about the inbuilt hardware. He does not need to know anything about a software. So there are built-in functions for all these, and one need not know the hardware and software details. So because of that, Arduino has become very popular for very fast product development. So this is the smallest Arduino board. It's called Arduino Uno. It's very popular, and popularity of Arduino has made many companies to design Arduino compatible boards. That means the wiring of these boards, even though they're high-end boards, the wiring will be in the same form. The pin configuration will be in the same way as that of Arduino. So school children can use Arduino boards. They don't have to know much about the hardware. So India government has a program for school children. Many of you must have heard of it. It is called Atal Tinkering Lab, where students work on electronic products. So Arduino platforms are used here because you can't expect a school child to know about microcontrollers, hardware, software, and assembly language, etc. So Arduino has become very, very popular. So if you want an engineering student to know the hardware, you should not allow him to use Arduino. So this is a typical Arduino, pinout diagram. It's all standard. And in this case here, the processor used is Atmega, but there are other versions of Arduino beyond Arduino Uno. So whenever we use, so talking about processors and peripherals, we need to know about sensors and actuators. So for that, MEMS technology is widely used and everybody can use it. It's easily available. You have, so look at this. This is a typical mobile phone. This is a mobile phone. What does it have? It has a power management module. Then it has energy storage module. Then it has RF module and signal processing module. So if you look at it, it has many systems. It can have Bluetooth, then many other types of communication like Zigbee and such things are available. But here I'm just focusing on this part. This part says that you have accelerometers, proximity sensors, magnetometers, gyroscopes, light sensors, acoustic sensors, pressure sensors, then humidity sensors. All these sensors are in the mobile phone. Why we have been able to use such a system is because MEMS sensors have become very cheap and very miniature, very small. That's why we're able to use them in all sorts of embedded systems. These are systems in a typical mobile phone. So these things I've just mentioned. Then for an embedded design, software is very important. 70% of development costs are for software. So suppose your student gets a job in an embedded company, the probability is that he will be doing software development rather than working on hardware. So software is very important. And what's the state of software? The most popular languages are C and C++. Even though there are high-end tools, finally they will have to convert into C because C is it's not superfluous. It gives the best is assembly language, but then it's very difficult to code in assembly language. Only in special case it used. Then the next most efficient language is C and C++, and that is what is encouraged. There are things you have Python, etc. for speed of program development, but still C and C++ are the most popular languages in embedded systems. Then they have a word called ecosystem. Even if a company develops a processor, it will be useless unless the company develops what's called an ecosystem. Ecosystem means they should have the debuggers, real-time operating systems, compilers, integrated development environment, and they should have all sorts of programming support. Then only you'll be able to use their processor. So when a processor is developed, its ecosystem also should be developed. Otherwise, we won't be able to use it. Just having a bad processor doesn't help us in any way. Then all devices you have to have connectivity. That means we should have mission-to-mission communication through wired or wireless technology. Okay, so there are many communication protocols. The last important thing about an embedded system is all embedded systems need an OS. Why do we need an OS? For a simple application like a temperature monitor, we may not use an operating system. But when there are many tasks in a system and there is conflict of interest, then we need an OS. Why do we need an OS for a computer? Because there are so many things, tasks working. Now, why do we need a mobile phone? There are many tasks. So to manage all these jobs effectively, we need an operating system. And there should be these operating systems work on priority. So important jobs are given priority. For as an example, suppose you are listening to music and a call comes. Immediately your music is stopped and call is taken up. That's because the priority is given for the call, and that is supported by the operating system. There should be an operating system to make sure that your music is stopped and a call is taken up. And Linux is a very popular OS in the field of embedded systems. So if you know Linux, you can do very well in embedded systems. And if you know Android is based on Linux. Android is very popular and it's based on Linux. Conclusions. So I'm just concluding about the embedded system part. So the other parts remaining. So an embedded system as an electronic product, any mechanical product with electronic control also will have is called an embedded system. All factories and defense systems and flights have electronic controls. The current trend is for interconnected embedded system, that is connected through some communication protocol. So the protocols may be Wi-Fi, Ethernet, Bluetooth, Zigbee. There are many other protocols also. And so we are going on to the next topic. The next topic is the trends. So I hope all of you have got some idea of the basics of embedded systems. Now we go into the trends, the current trends. We can't just stop with embedded systems as it is now. Things will change. The world is changing. So new technologies are coming up. And the new technologies, you'll be hearing a lot about IoT soon. I'll just mention the IoT plus ML. They are not separate. They have to, everything should go together because currently machine learning, artificial intelligence, etc., become very, very popular. You can't get away from all these things. We have to learn about artificial intelligence and machine learning if you want to survive in a technical field. So we'll first talk about AI. AI is actually what is meant by AI is called artificial intelligence. Artificial intelligence, it means that we are trying to get intelligence artificially from a machine, and the machine is supposed to behave like a human being in terms of intelligence. And what is the real reason why we want artificial intelligence? Why can't we be satisfied with whatever intelligence that's already available? Now think about the industrial revolution long back, 17th century, 16th century. At that time, all work was manual. There was no washing machine, there was no, let's say, grinder. There's not such things were not there. Then the industrial revolution came and many new machines came. What happened is humanity was freed of physical drudgery. So now we don't have to do any grinding physically. So there's a grinder to do it. So industrial revolution freed up a lot of human from physical drudgery. Similarly, AI has the potential to free up humanity from mental drudgery. That means if we have a problem to solve, we don't have to spend lots of time calculating and predicting it by ourselves mentally. Instead of that, you give it to an AI algorithm, it will give you a result immediately. Okay. Suppose you take a lot of factors and we don't know whether the output of that, should I do this or should I do that? That answer will be given by AI. Okay. AI has uh, AI has the potential to free up humanity from a lot of mental drudgery. Our computation has been reduced because AI will give you the answers. And when we talk about machine learning is just a subset of AI because subset in the sense that if you take AI as a whole, AI will have other things like search algorithms and many game playing algorithms. All these things are included in AI. Machine learning is a subset. We consider a small set of algorithms as machine learning algorithms, but they're all part of AI. To give you a brief introduction to AI, as I am talking about machine learning. Machine learning, what we want to do is we want to make machines think and work in the way humans do. Just like humans are working, they should think like a human and work like a human. In some cases, machine learning algorithms are better than humans. In some cases, machine learning algorithms don't perform as good as humans. Take a case of human face recognition. Human beings are very good at face recognition. If you see a person, immediately the human will know, have I seen him before, have I not seen him before. The human will recognize or not recognize immediately, but to make a machine do it, it's very difficult. I mean, it's a lot of work involved. Human beings do it automatically. Machines have to have a very big algorithm, have a very large data set to do it correctly, but machines are very good at it. But some applications machines very good. You know that repetitive work machines are good, but reasoning work machines are not that good. But machine learning is meant to improve on that. Machines are made to think like us and work like us. And there are fundamentally three different types of machine learning. Fundamentally, there can be again subsets of this. I don't know how many of you know about machine learning. I'm just giving you a introduction. So if you already know it, just bear with me. So the first type of machine learning is called supervised learning. Supervised means there's a teacher to teach you, and using the help of a teacher, we are learning. So as an example, I give you again. I want to do face recognition. How does the machine do face recognition? Machine does not have any inbuilt capability. Machine has to be taught. So first, you give us a number of faces to the machine. You load the machine with a number of faces. So I have 10 photographs of mine put there under the name Laila. Then 10 photographs another person and give the name, say Ashwin. 10 photographs of another person named Liz. So all these names I've given. So what we have, machine has been told that these 10 photographs are of Laila, these 10 photographs are of Ashwin, these 10 photographs of somebody else. So the machine has been given a label. A label is given. That is, this is this person photo, and that if you see this photo, you identify at this person. That label should be given. So the data is given with the data as well as label. In supervised learning, the data and labels are provided. So you give 100 photographs, 100 people's 10 photographs each, and the names of these 100 people are also included. So that is a label. The names of the people are the label, and the photographs are the data. So after teaching the machine all these things, so what the machine does is machine learns these data. Once the machine learns, we say the machine has been trained. After you train the machine, you give it a new photograph and tell the machine identify who this is. So machine will look at its database and find that this face is looking similar to one of the photographs there. It will say that it's the name, gives the name of Ashwin. Then immediately it can be either wrong or it can be right. Okay, so that is the way it is. So the machine has two phases. One is called the learning phase, or we call the training phase. The machine is trained, and the second phase, testing phase. You give a new photograph to it, and it will either say it is within the database or say, no, I haven't seen this person before. It is not in the database. So that's the test phase. So supervised learning is when we give data along with labels. Now, unsupervised learning is when we don't give the labels, we just give data. Again, I'll give an example. Example is I give the size of many t-shirts. The size, say it is 20 inches to 42 inches, 20 inches, 21 inches, t-shirt shoulder sizes. I tell the machine, divide it into 5 different classes of double XL, triple XL, XL, large, medium. So the machine has no knowledge of any of these things, large, etc. But what the machine will do it, it will cluster it into 5 sets. The algorithm will make 5 clusters based on some method, and the cluster which is having the lowest values, we can say it is medium. The machine does not know anything what is medium. We will say that is medium. The cluster which has the largest t-shirt sizes, we can say it is triple XL. Okay, so the labels are not given, but the machine will cluster it. Or there are other methods also. I'm just giving a basic, simple example. So that is unsupervised learning. The third is called reinforcement learning. Reinforced means you keep on telling the machine something, just like we do with the children. When they do something wrong, we tell them that is wrong and you're going to get a punishment. If they do something right, we give them a reward. So when rewards are given, human beings have a tendency to do things which will give rewards. So if you are given some errand and you are given some money as a reward, you will be happy to do it again. But suppose if you do something and you're given a punishment, you won't do it again. So reinforcement learning is like that. If the robot is moving and you tell a robot starts moving and it falls, immediately the robot gets a penalty. That is, it's given a negative reward. So the robot will not attempt to do it again. It will do some other mechanism. So this is by learning by itself. The reinforcement learning, that the machine learned by itself. Nobody teaches it. By giving it rewards and punishment, the machine will learn. That's called reinforcement learning. So these are 3 different methods of of machine learning. But one method of machine, the most important issue with machine learning is that for all these cases, except for reinforcement learning requires a lot of computation, These two methods require a lot of data. Suppose you want to recognize from a set of 100,000 people, what will happen? You need to give the data of 100,000 people. So much of data is involved. So data, it is all these machine learning algorithms are data intensive. So how to handle this data is the biggest problem of machine learning. And looking at the algorithms, the first algorithms, all these are algorithm machine learning, logistic regression. I'm using for a simple classification task. Classification means say whether this is right or wrong, yes or no, is it a dog or a cat, this classification. For classification, these are some of the methods. And the above methods are called classical methods of ML. Classical means they're the older methods. K nearest neighbor, decision tree, support vector machine. All these are older methods. They are classical and simpler methods. But the newest method is called artificial neural networks. And when these neural networks are very large, we say deep learning. Now, if you look back at, I'm not going to discuss deep learning much. What it does is it is supposed to mimic the processing activities of a brain. So this is the brain which is getting input from various sources, and accordingly it is making a decision. So deep learning network will be like this. It will be taking inputs from the environment, some data it is getting. There will be a number of connections between the different neurons. This is the input neurons, these are the output neurons. There will be hidden neurons, all of them are interconnected. And depending on the input, the output, there should be some correct output obtained. Okay, so this is the deep learning network. And if you look at it, this is one input layer and this is one output layer and one hidden layer. But a practical deep learning network will be having many, many layers. So here the output is only one, but see, you have 4 input neurons, many, many hidden layers. So this hidden layers can go into hundreds and thousands for a very large deep learning network. So what actually the algorithm is that usually you feed some input and you expect to get a correct output. But then usually the output will be wrong. Then this wrong information, the fact that is wrong, that error will be propagated backwards through these interconnections. And then error will be noted. And based on that, weights will be changed. Weights means all these interconnections have a weight, some weight. So these weights will be changed according to the error. So as the error changes, the weights also will be continuously changing, and there will be a propagation of error from the output to the input. And this algorithm is called back propagation. So this back propagation algorithm requires a lot of computation, actually, immense amount of computation. That's the whole problem with deep learning network. So machine learning was known long, long back. Many 50 years back, machine learning is known. And artificial neural network was also known long back, maybe 25 years back. 25 years back, it was known. I was teaching artificial neural networks even 25 years back, or 20 years back, let me say. It was gaining popularity. I even guided a project in which students were supposed to recognize faces using neural networks. But then once the theory was developing, suddenly it's lost popularity. Why? The point was that lots of algorithms were developed, but how to run these algorithms? Fast hardware was not available. The computers available at that time were not good enough to run these algorithms. So the fast hardware unavailability slowed down the speed of machine learning development using deep learning. Now what has changed? Now what has changed is that fast hardware is available. So now deep learning is coming back at a rapid rate. Now fast CPUs and faster GPUs are available. GPUs are very important now. GPUs means graphical processor units. So I'm just showing a figure here. This is a CPU architecture. Okay, CPU means the CPU have 4 cores, but within each core, the computation will be done in serially. All 4 of them can work simultaneously, 4 cores, and they can all run programs. But inside each core, the processing will be done serially, sequentially. In contrast, look at the GPU. GPU here, you have multiple GPU cores. Here I'm showing only a small core. This has 32 cores here. So 32 threads can run here. 32 threads here, 32 threads here, 32 threads here. You have multiple activities running in parallel. And a deep learning network, if you have multiple parallel processing, it can be very efficiently done. So if we have a hardware in which there's a CPU plus a GPU, the whole system will be very fast. So that's the whole beauty of CPU and GPU. And now all machine learning architectures wants good CPU, and if a GPU is available, it makes it doubly fast. So the hardware has developed, and that's why machine learning has become so very powerful, so very useful, so very popular these days. Now, we are not talking about CPU or GPU or machine learning now. We are talking about embedded systems. Now, why we are talking about machine learning and embedded systems is because instead of using a traditional uh, embedded algorithms, we can use we can use machine learning in embedded systems. All your algorithms can be run in machine learning algorithms. Suppose you can fit it into your embedded systems, won't it be good? Because machine learning algorithms are very good, embedded systems are very good. So can't we put it together? Why use embedded AI or why use embedded ML? What is the encouraging factor? The encouraging factor is that sensors and MCU prices have plummeted, gone down. Okay. So we can afford to buy these things. And more companies have tried to take advantage by adding sensor driven embedded AI to their products. So that is what they have done. You add AI to their products and you can put all your AI into your microcontroller unit. That's what we're going to discuss now. Can we put all this uh, high-end machine learning algorithms into embedded systems? Can we do it? What are the problems? That's what we are going to say. So, what is the encouraging factor is that now embedded AI, that means hardware in which embedded systems are running. For example, automotive is leading the trend. In a ordinary vehicle, we have around 100 sensors. We have 30 to 50 microcontrollers, 1 million codes, and 1 TB of data are being generated per car. So this much of work has to be done. This much of hardware is done. This much of software is done. Then luxury vehicles and autonomous vehicles, they'll increase number of sensors, number of processors. All these are much more. And if we use machine learning algorithms, things can work much more efficiently. So what they say is traditional engineering, what we had used all these years, compared to machine learning algorithms. If you want to do with all these, say 30 to 50 microcontrollers and 100 sensors, use them simultaneously, the best is to use machine learning algorithms rather than your old classical algorithms. So if you want to use them, then it will be best and then things will be easier. With modern tools, including new options of machine learning on signals, the whole system will become fast and easier. So why do we use machine learning? Because there are so many machine learning tools now which are optimized for signal problems and embedded deployment. It can cut months or even years from R&D cycle. So if you want to do something, you have to do research and development. That used to take a long time. But the current machine learning algorithms, machine learning tools have enabled systems to cut R&D cycles. Your product design cycle will be cut. You can upload or you can launch your product into a market much faster than previously because of the advantage of machine learning algorithms. Then some things which you couldn't do earlier with traditional engineering methods, we can do now because of the new methods in machine learning. The only thing is we have to use different approaches for different problems. Depending on the problem, you choose your algorithm, choose your method, choose your solution. That is what we need to do in this field. So, what one more topic we have is how to include IoT. It's also coming into this. So, machine learning, can we use machine learning in embedded products? That's what we'll land at. Now, in between, I had to talk about IoT. I won't talk too much because we have other lectures on it. I'll just talk briefly some introduction to the basic architecture because the next lecture will be about IoT and you will know about cloud computing and details about it. Here, I'm just talking about looking at it from the hardware aspect. Now, looking at the hardware aspect. Now, first, to start with, I have to define what is IoT. So, if you look at this figure, you can see a person. He has a number of sensors connected to his body. Okay, what are the sensors doing? They are sensing this motion, sensing is ECG, how fast is running, movement of his legs, left leg, right leg, hand, all this motion is being sensed. And then nothing much is done, they're giving him results. And what is the internet? Why is he using the internet? He's using the internet only for his personal applications. Okay, so actually the people connecting to things and people connecting to internet. So previously it is called internet of people. Internet of people like us, we are always connected to the internet, and then we do work with internet. We are getting data from internet, we process it, nothing else. That is, humans are connected to the internet. Now the word, that's internet of people. Now we have a word called internet of things. Things means some physical thing, an object, physical object. So what is IoT is meant? IoT is when objects can sense the environment. Objects by themselves, they will sense the environment. They communicate with other objects without human intervention. They update their daily schedules, and then that scenario we say IoT. That is when IoT is at work. Objects, they don't need human intervention. So smart objects can interact with humans. They are likely to be even more interacting with each other without much human intervention. We can interact, the things will interact with humans, but mostly they are interacting with other things without much human intention. Then we say it's IoT. So IoT is where things interact automatically with other things. So we have an IoT scenario. We can see many things. All these are things connected to the internet. Just take the simple case of refrigerator. Refrigerator, as of now, we don't have connected refrigerator, but suppose we have a connected refrigerator. We can imagine a scenario when there are sensors in your vegetable tray, sensors with Wi-Fi capability in your vegetable tray. When the vegetable tray is getting empty, then the sensors sense it, automatically send a message to your vegetable shop. The vegetable shop will get the message, and of course, through human intervention, otherwise, it will send vegetables to your home. And probably human intervention may be necessary to stack it into your refrigerator. But communication, sensing, sending messages, everything is done automatically by the refrigerator. So this is called a connected refrigerator or a smart refrigerator, and it is using IoT, Internet of Things. So all these are examples of Internet of Things. Wearables. Human being has many wearable devices, medical devices connected to his body. Data is going somewhere through the internet to a doctor's place. The doctor has some automatic hardware which will software which will tell what's the medicine you have to take. Automatically, information comes to him. Then that is one scenario. You have connected cars, connected homes, connected cities, smart cities, you can say. So all these are interconnected. They can do their work without much of intervention by human beings. The only thing is you need some internet connection. And before the internet connection, you can have other small connections also, like Zigbee connections there. And the central part of the Zigbee will connect to the internet. These are all possibilities. Now, these are the components of a smart home. So refrigerator is smart, garage is smart, AC is smart. They will work. Smart oven in the morning at the correct time. The oven will heat up whatever is there, but you should supply the bread. Gate will open automatically. Doors will on automatically when it is necessary. When some sensor input comes, it will open. Here, when sensor input comes, it will open. When sensor input is removed, it will close. So all these things are done smartly without human intervention. And the connectivity is by internet. Then it will be an IoT enabled system. It's only a small system. You can have a smart city with these ideas. Now, coming to the technical part of IoT, and one aspect that we'll discuss, a standard IoT will have a architecture like this. So here, these black dots are called end devices. End devices. What do the end devices mean? End devices are the sensors and the microcontrollers to which the sensors are connected. They collect data from the environment, physical data from the environment. They're called end devices. End devices will have microcontrollers. They'll be having the sensors. They'll be having the actuators. As an example, suppose this is for a smart garden. Sensors will measure whether the soil is dry, and then possibly send data to the internet. Internet will check whether the soil is too dry, and then tell the sensors that tell this microcontroller that the soil is too dry. Then the actuators connected to this unit will immediately switch on the motors and water will flow. Pump will start. Okay. So the end devices will have sensors, actuators, and microcontrollers here. That's what the end devices. Then the data from the end devices will be sent to the cloud. Cloud means internet. In between, there is something called a gateway. This gateway will be a router or some such device which will take the data and pass it to the internet. This is called a gateway device, or it's called an edge device. This orange block is called an edge device. It is the edge of the cloud. That's why it's called an edge device. See, this edge device is a device which provides an entry point into the network. Network is the internet. Okay. And the internet is what we call cloud. Now, this edge device usually, and no, sorry about talking about edge device. I told you it's a gateway, some sort of a router or something like. Let's see what doesn't matter for the moment what it is. And we want to run. Suppose we want to run machine learning algorithm on a system. We want to run a machine learning algorithm. So what happens is that IoT, and we want to run IoT. This is an IoT system, and we want to run machine learning algorithms. So your end devices collect all the data, but they can't store all the data here because the microcontrollers don't have much data storage facility. They don't have much data computation facility. So what they do is take the data, send it through the edge into the cloud. Okay, they send it to the cloud. And the sensor node, as I told you, it won't have storage for data. It cannot do computation. So everything is sent to the cloud. The cloud will do the computation, give a result, and send it back to the end device for actuation. That will be the scene. Now, one problem with such a case is that suppose we do all the computation here. The critical part of this network is your internet connection. So internet connection is slow, then what will happen? This whole process will be slow. If the internet connection is not reliable, the whole process will be unreliable. So internet connection is very important. It can run in the cloud, but the speed of the internet may be the limiting factor. Then one more thing is security. Security issues are more. Suppose all your data is in the cloud, somebody can hack the cloud. It's easier to hack the cloud than to hack data from your end device. This end device is your own thing. This is common, maybe common. At least cloud is more like common to everyone rather than end device. Only you are aware of it. You have access to it. But a cloud in a white node can be accessible to everyone. They can hack it and get it. So when you do computation in a cloud, security issues are more. Okay. And for real time or security critical systems, doing computing in your, sorry, doing computing in your cloud is not very good, okay, because of security and reliability issues. Then the next option is, why don't you do your computation in the edge device, this orange device, that is the edge device. Computing should be nearer to the end device. So let's do it in the edge, maybe in the edge device. If you do it here, then the internet connection is not very critical. This is the internet connection. So it is safer, it is more reliable. Then in that case, your edge device can be a very high-end device like a PC or a Raspberry Pi or something like that. So you can have a very good computation done here. You don't have to go to the cloud or to the internet. That is called edge computing. You do all your computation on the edge. A better computation method is called fog computing. You know what is a fog? Fog is something which is closer to the cloud. Cloud is high up in the sky, and the fog is somewhat below the closer or down closer to the earth. So whenever you do a computation, the end device, then it is called the uh, fog computing. Here, your algorithm is run in the end device. That is here, these black dots. Or another option is because end device is not high end, what you'll do is some layers of the machine learning algorithm you do here, some layers you do in the edge device, some layers you do here. For example, deep learning, you have many layers. Hidden layers are there. Some part of it you do here, some here, some here. So at least uh, something is saved. But what's the advantage here? One method is do it like this. Suppose you have a machine learning algorithm, deep learning. The first part of a deep learning network is called feature extraction. So end device can do feature extraction, take the features and send it to the cloud. So the features, once you send the features to a cloud, nobody can do anything with the features. The data is always here. So security is not compromised. So what you do is you do your feature extraction here, computation here. So that is, we are doing fog computing, or we can do edge computing, or we can do some amount of cloud computing. So everything together will solve your problem. So finally, suppose you want to do fog devising alone, or you want to do edge devising alone, edge computing alone. You want to do everything in end devices, or you want to do everything in edge devices. You don't want to go to the cloud. So what is the problem? One problem is this is not a very good device, not a compute intensive device. This is also not that much of a compute intensive device, as it is not as good as a cloud computation. So what you do is you can do things at the end device only if the end device is very powerful. So what should you do? You make the end device to be powerful devices. That will be costly. So the problem with end devices, they are battery powered, must have low power consumption. They may have limited ROM. They may have to support RTOS. It will be very, very difficult. So what you need is you need to have this end device to be smarter. Then what you can do is you can have single board computers like SPCs, etc., and powerful boards can be used here. Okay, then device. That's only one method. Or if you can't do here, do it here. Raspberry Pi can be used here. Don't send much to the cloud. That's an advantage. Now, in a paper that I've given as reference, they've used some of these boards as end devices. Okay, hardware has been used. Some Arduino Uno, Raspberry Pi, then you have some STM boards. These are not as low in computing like an 8051 board. So you can use them as end devices or edge devices. That's one suggestion. Now, finally, I'm just coming to the conclusion that suppose you want end devices to be powerful and used as fog computing devices, then the end devices should have enough memory, should have low power consumption, should have small execution time, should have enough data width, like instead of 8 bit, they should be 64-bit or 32-bit. They should have floating point capability, they should have GPUs. Are these things available in a hardware now? Do we have an ARM board with all these things? Actually, no. It's very difficult to get hardware like this. But what I'm telling you is now things are changing. Things are changing. Many companies have come up with boards with such capabilities. Of course, the power consumption will not be very low, like 2 watts or something, but still they improved. So what you do is to solve these machine learning issues for embedded devices, new hardware, new ecosystems are coming up. Finally, these are the uh, 3 boards, some boards which are available. One board is NVIDIA's Nano board. It is a machine learning board with GPU. It has only 5 watts power. Next, you have a Jetson board TX2. This has only 7.5 watts. It's a supercomputer like board with GPU. Third, you have one more board called the NVIDIA Savior Development Kit. And these are the boards which can be used as end devices or edge devices. Actually, in my college last semester, we started using the first 2 boards, but the students were not able to complete the project because finally this pandemic came and they had to go home. So the boards remained in the college and students were at home. So we could not complete it, but we hope that next semester or the semester after that, we'll be able to use these boards. So it's actually we can buy all these boards. Boards are not expensive. Nano is only 9,000 rupees. It's quite a big amount, but still. Finally, last one. There's an Intel Neural Compute Stick. It's a USB device. You can use it at the edge. This is also available. So I think if there are any questions, I don't know how questions can be asked. I'm concluding. I'm just trying to put ML and IoT in ML now.
Thank you, madam. And it has been a wonderful presentation. And actually, the presentation was possible in the most simplest manner. And I think it has been comprehensible for all the participants ranging from various disciplines. But yes, madam, the questions are definitely there in the chat box of YouTube, which are also there here. And I would request our session coordinator Mr. Shudhanshu Sharkar to read out the questions to you.
Okay.
Thank you, madam. Madam, the
Yes.
session was excellent one. It was really very informative, and this is really wonderful session.
Okay. Thank
So,
you so much.
some participants asked a few questions. The first
Yeah.
question from Mr. Himadri Shekhar Barman. He asks that what is the difference between embedded system and PLC system?
I am not very familiar with PLC because PLC is basically what I understand is something which is not very familiar to me. It's actually something is being done with in the electrical department, but PLC is also an electronic system and it's an embedded system. There's no difference. PLC is an embedded system as well because it has electronics, it has software, it has its applications. So it's an embedded system. Okay, hardware. It is not a general purpose system. It's a very general. It's a specific system. Isn't a PLC with a specific application? Isn't a PLC something with a specific application? So it is part of the embedded system scenario. Okay. Embedded system is not a very it's a big class. Everything we do in electronics with hardware, software, mechanical, it's an embedded system. Okay. There's no difference. PLC is also an embedded system. Okay. Only the PC we are taking out and saying it is not an embedded system. Everything else is an embedded system. Okay, I hope that will be okay.
Yes,
Yeah,
madam.
yes, madam. Okay. Next
Madam.
question.
Next question is, ma'am, where are ARM processor can be used other than mobile phone?
No, actually, ARM processors are used extensively everywhere. If you see your tablet, that electronic tablet, commercially, all the new applications are with ARM processor, embedded application. In your lab, suppose your students want to do some embedded project, and if they want some high-end applications, okay, then they will definitely be using any ARM processor. There are many boards like you can say Texas Instruments Tiva board. All these things are available. All applications are done with high-end applications are done with ARM process nowadays. Okay, so if you're using a camera will be most likely having an ARM processor. Anything will be having a high-end application. Everything will be using an ARM processor. You're not aware of it. That's all. Okay.
Now, there is another question. One of our faculty members has asked.
Yeah. What's the question?
Yeah. Is it binary compatible with 8086? Is it the question?
No.
Am I correct?
No. It is not compatible. ARM has its own ecosystem. When you want to do ARM, it has its own system. 8086 is a microprocessor. ARM can work only with other ARM processors. It's not compatible. It's entirely a different processor.
Okay, madam. There is another question. Yes, Shudhanshu, please. Yes.
Another next question is, ma'am, what OS is used for ATM?
What
OS,
operating system?
Operating system is used for ATM.
No, I am not aware of it because that's not public knowledge. Now, every system like that, they will be having a very small real-time operating system. They're generally called real-time operating system. There are many small real-time operating systems which are not known in the public domain. Okay, so every system will have its own RTOS. We need not know about it. And it will be very small RTOS. It's called RTOS, real-time operating system. There are hundreds of them in use. Each company will have their own favorite thing. It's a very small software.
Okay, ma'am. Next one is, what is core in processors like core 3i, 5i, etc.
No, I have to understand the question. What is
core in processors?
Code, a COD.
CORE.
A core means, so whenever we say core, it is the computing engine. What we call is the computing engine. That is your ALU and CPU. Basically, your ALU and bus interface. That part is called the core. Okay. Only the computing part, computing engine is called a core. Everything else in a microcontroller, if you have peripherals like timers and serial, they are called peripherals. The core is just your computing engine, computing part. That's called core. Okay. Am I clear? Is that enough? Any more explanation needed?
Yes, ma'am. Next one, one participant asked that cost of ARM processor.
Yeah.
Any idea? Yes, yes, ma'am. Cost of ARM processor.
Cost means
Yes, ma'am. Cost.
suppose you take this Freedom Board, FRDM board, you can get a small FRDM board with Cortex M0 in the range of 800 rupees. Okay, 800 rupees you can get a small board, for development board for students to work. Then if you use high-end Cortex M7 board, then probably it will be in the range of 2000. But ARM processor, you can get very small boards with 700, 900 for academic applications, all these things. You just have to identify which board you want. If it's an STM board, ST microelectronics boards, you have boards in the range of 900 to 5000, 6000 boards available. You just identify which board you want. So you have boards even in the range of 700. FRDM boards, Kinetis board. You just search, you'll get very low, very cheap boards available. Okay. Okay.
Okay, ma'am. Thank you, ma'am.
Okay. So thank you for the patient listening. I hope I have made myself useful. Thank you very much. Shall I sign out?
Thank you, madam. We'll be sending you a certificate of appreciation in your mail from our end, and I will contact you for other formalities as well.
Okay,
and I hope that you will be joining us in our future programs as well.
You just give me when is it? At what time?
I will send you the mail, madam.
Okay. Okay. Is
Thank
it today?
you. No, madam. It's not today. It's after another week. I will send you the mail. Okay.
Okay. Thank you. Thank you very much.
Thank you, madam. Thank you for your precious time.
Okay. Thank you for your patient listening. Okay. Right.
Thank you, madam. Okay. Okay, so we have Professor S.D. Madhukumar, who is our next distinguished speaker, and he has joined us. So I would take the privilege of reading out his profile in brief. Professor Madhukumar is presently in the Department of Computer Science and Engineering as a professor at NIT Calicut. For the past 29 years, he has been working in the department. He was the head of the Computer Science and Engineering Department of NIT Calicut during 2012 to 2004. Presently, he is the Dean of Students Affairs of NIT Calicut. He received his PhD in Computer Science and Engineering from IIT Bombay. Earlier, he did his Master's in Computer Science and Engineering from IIC Bangalore. He has more than 70 international publications to his credit and has produced 10 PhDs and currently guiding 4 doctoral students at NIT Calicut. His research interests include cloud computing, big data analytics, software engineering, and DBMS. He is a senior member of IEEE and a member of ACM USA. He has been the track co-chair of the cloud computing track of the ACM Symposium on Applied Computing since 2010. He also serves in the editorial board of several international journals, including ACM ACR. So more details of Professor Madhu can be found at the website of NIT Calicut. Today, he will be assisted by his research scholar, Sri Jay Shuraj J. Mr. Jay Suraj J is also pursuing his PhD in the Department of Computer Science and Engineering at NIT Calicut, and he has received his BTech in Computer Science and Engineering from Kerala University, India in 2012, and MTech in Computer Science and Engineering from the same university in the year 2015. His research interests include protocols for computer networks, wireless networks, and Internet of Things. Now, with these words, I would like to hand over the session, Professor Madhukumar. Welcome, sir, to our program.
Yeah, thank you, ma'am. A very good morning to all of you.
Good morning, sir. Good afternoon.
Yeah, good afternoon. Yeah.
Yes, sir.
Hope I am audible to all of you.
Yes, sir, you are audible.
Yeah. So, how is the climate there in West Bengal?
It's hot and humid today, sir.
Okay, so it is raining heavily in Kerala, in Calicut.
Yes, sir, I heard.
We are facing a flood-like situation. So, yeah, thank you for giving me an opportunity to address the faculty members and research scholars from West Bengal. So, this is actually an introductory lecture. This session will be handled by me and my student research scholar Jay Suraj, who is working in the area of IoT. He is in the third year of his PhD program. So he is actually a person working in the area of Internet of Things. So I will be giving an introduction, and I will hand over to Sri Jay Suraj. Jay Suraj is also a faculty member working in a college. He was working in a college in under government of Kerala. So currently he is doing PhD here. So I am starting my presentation.
Yes, sir.
I hope the screen is visible.
Yes, sir, it's visible.
Yeah, as I told, this is actually an introductory lecture on Internet of Things. So we will be covering the basics of IoT and the architecture and the road ahead. That is actually the research directions or research opportunities or research problems in the area of IoT. We believe most of you are research scholars, so there are people looking for PhD problems. So the third part of this lecture, that is actually the road ahead, is actually focusing on the emerging areas in IoT. So the second part is on the architecture or the technical side of IoT. So these two sections will be handled by Sri Jay Suraj. So these are our email IDs. So as with the previous speaker, we won't be able to answer all questions due to lack of face-to-face connectivity or interaction. So you can note down our email IDs. So if you have further queries at the end of the talk, you can probably mail to us. So here is my email ID, and this is email ID of Sri Jay Suraj. So as I said, there are three parts for this talk. First is actually the basics of IoT. The second part is on the architecture, the protocols used in IoT. And the third part is on the research areas or emerging hot topics in the field of IoT. And finally, we will also be listing few conferences and important journals where you may find more information about IoT. In the case of computer science, more than journals, people give importance for leading conferences. So it is very important that we know the conferences in this area. That is why we have included the list of leading conferences, important conferences in the area of IoT. So this is the thing. So I will be handling the first part. I will give the introduction on IoT, and then I will hand over to Jay Suraj. So the basics of IoT. So you might have seen this particular slide. What is actually happening in a minute in the internet? So a minute is actually 60 seconds, as all of us are aware. What are the things that are happening in the internet in a minute? So that we call as internet minute. This is actually a diagram which is or a figure which is little older. So the values may definitely be much higher or it might have gone high. Any idea how many emails are being sent in 1 minute in the internet? According to this picture, it is 204 million emails are sent. Definitely the values might have gone high now. In a minute, more than 200 and maybe 300 million emails are sent. And in a minute, you can see that according to this picture, you have more than 1 lakh tweets happening in the internet. And if you look at the Facebook, how many people are logging in the Facebook? I mean, it is again huge numbers. So there are a lot of things which are happening in the internet on every minute. So what is the relevance of that? Every activity on the internet is pumping lot of data, or it is generating huge amount of data. So data is being pumped into, or it is being poured into the internet. So how to handle or how to keep track of all these things? So you have YouTube videos, you have tweets, you have Facebook posts, you have searches, you have emails, and you cannot imagine the type of data or the different forms of data which is being poured into the internet. So now, in today's world, data is actually the currency. So if you don't have the right data at the right moment, you will not be able to do anything. If you are, the time has gone where one person is called a millionaire or a rich man if you are having more money. In today's world, if you have more data or if you have the right data, you are going to be a rich person. So data is actually the currency in today's world. So you may be wondering, or you may already be aware of the importance of data. Can anybody guess what is the importance of data? In today's world, you are having machine learning or you are trying to have smart applications. That means applications which can learn from old data and which can predict what is to be done in a given situation. So in the machine learning applications, if you want to train something, you should have the old data. So without data, you cannot make an application smart. So in any case, data is a very, very important thing in today's internet scenario. So IoT and data or the so-called big data are going hand in hand. Let us see what is the current scenario of internet. So internet technology has been evolving ever since its inception. So we had IPv4 and now there is IPv6. So internet is increasing, or the total number of people who are getting connected or total number of machines which are getting connected into the internet is increasing minute by minute. In the year 2010, the number of internet-enabled devices per person went above one for the first time. So the total number of machines connected to the internet has gone it has gone much higher than the population on the earth by during the year 2010. It is estimated that the number of such devices may go up to 4 per person by the year 2022. That is, the total number of internet-enabled machines or the IP addresses will be 4 times the total population on the Earth's surface. So estimates also suggest a threefold increase in the annual global IP traffic. So when more machines are connected into the internet, naturally the traffic also increases. The network traffic increases tremendously in the internet. So machine to machine, M2M connections are likely to account for 51% of the total by 2022, which is a sharp increase from the value of 34% in 2017. So normally when you say internet, it is actually the connections between the people, or it is actually the connection between the different IP-enabled devices. Now the machine-to-machine connections is likely to account for 51% of the total internet connections by the year 2022, which is much higher than the 34% which was the situation in 2017. Now, what contributes to such an increase in traffic? Such an increased traffic can result in severe scalability as well as traffic congestion issues in the internet. So this is a hot area. How to deal with the traffic congestion in the internet? The reason behind such an estimate is the ever-increasing number of IP-enabled devices. Now, everyone is having a mobile. So there are people who are having more than one mobile. So you have two smartphones and you have a laptop and you have a desktop. So one person itself is having 5 IP-enabled or 5 internet hooked or internet connected devices. By the year 2022, the total number of IP-enabled devices is to reach about 4 times the total population at that time. So this is the situation. So just give you an idea regarding how much load is coming on the internet. A solid reason behind this increase is the latest innovation which allows even everyday things to get connected to the internet. The innovation called the Internet of Things. Now, we are talking about a technology or a situation where anything can be connected. So the so-called things, you can see the uh, double quotes here. Everyday things can be connected or it can be hooked into the internet. So Internet of Things or IoT. So IoT is regarded as the latest and trendy innovation in the information and communication technology domain. In the ICT domain, IoT is the current trend. IoT can be defined in simple terms as the inclusion of everyday things in the global internet platform. So this is a simple definition. Everyday things which are connected in the internet platform is referred as IoT, Internet of Things. Two salient features of IoT are things should be able to communicate among each other with a minimal or no human intervention. So the things that you are hooking or you are connecting or you are plugging in the internet should be able to communicate each other with minimal or no human intervention. Things are designated as the end users. So on both ends, you have smart devices which are connected. So these things are designated as the endpoints of this IoT. IoT has been realized as a result of the constructive fusion of multiple technologies. So that is what we are going to see. What are the different technologies which are enabling or which has resulted in this IoT? So here we have a working definition for IoT. So there is no standard definition as such for IoT, but we can follow this definition for this particular talk or for this particular session. The Internet of Things is the internetworking of physical devices, vehicles, buildings, and other items embedded with electronics, embedded systems, embedded with electronics, software, sensors, actuators, and network connectivity that enable these objects to collect and exchange data. So we can see that IoT is the internetworking of physical devices, vehicles, buildings, and other items embedded with electronics, software, sensors, actuators, and network connectivity that enable these objects to collect and exchange data. So this can be a simple equation illustrating what is actually IoT. IoT is sensing plus communication plus computation. Anything, THING, anything which has got a sensing capability plus a communication capability plus a computation capability can be plugged into internet and it can be part of IoT. So anything, THING, anything which is having a sensing capability, a communication ability, and a computation capability can be connected and can be part of IoT. So IoT and big data, as at the beginning, as I have told, IoT and big data are very much related, interrelated. So a lot of data is being generated. People describe them as big data nowadays because of the huge volume and huge variety in which the data comes. It is referred as big data. IoT is not delivering full potential because of the data challenges. As we have seen that different types of devices or things can be connected into the internet, each of those things can also generate and contribute data into the internet or in the big data world. So better IoT data collection and analysis would deliver more value. So better IoT data collection and analysis would deliver more value. In the next slide, we see different devices or different things which can actually generate data. So data acquisition equipments in IoT. So you can see that GPS enabled devices, intelligent cars, smart cars, mobile computing devices, PDAs, mobile phones, intelligent clothes, alarms, window blinds, window sensors, lighting, heating, refrigerators, microwave, washing machines, all these things can be connected ultimately to the internet, or and all of these things can also contribute data. So they are all data generators, and we need to acquire, or they require data acquisition systems or technology by which we can collect data from all these potential devices which can be connected into the internet. So IoT in society. Now IoT is not at all a fantasy. It is already there, or it is already existing in some or other form in the society. What distinguishes IoT among other inventions in the ICT, information and communication technology domain, is its unprecedented social relevance. So especially in the pandemic situation, in the current pandemic situation, IoT can do a lot of things in the healthcare and related pandemic control activities. The complete realization of IoT can indeed pass on numerous benefits to the society. In the healthcare systems, in smart homes and smart cities, and in food security and sustainable agriculture, secure, clean, and efficient energy distribution, transportation systems. So these are some of the areas where IoT has already shown its presence. Let us see some points on each of these things. We are just introducing these things just to motivate you on the importance of this particular topic. So IoT in shopping. So this is already a reality. I mean, when you go to a shopping mall, it is very interesting, or it will be a fun for people to go and take or purchase the things. But when you are coming to the checkout counter or in the payment counter, you may find a huge queue there, a large queue there. So you have to wait for a long time in the queue till your turn comes. So people don't want to waste time in the queues. So IoT is very much used in automated checkouts. So when you take the items from the shopping mall or from the different shelves, automatically it will be counted depending up. I mean, there will be an RFID tag on the products, and the RFID network will collect the details regarding how many items you have taken, and the prices will be calculated accordingly. And when you come to the checkout counter, automatically your bill will be generated, or even the bill can be deducted from your bank account. So such shopping systems are already there, so that you are not wasting your time at the payment counter. Similarly, there are smart shelves. I mean, you have different sections or different shelves in a supermarket. You have a vegetable shelf, and you have a shelf where you have the cosmetic items. But people may take and put it in different places. So if some item is in a different place, or if it is in a different shelf, so there can be an IoT application by which it can say that this is in the wrong shelf. It should be kept in the proper shelf. So automatically the things will be kept in appropriate or in the suitable shelf. So this is actually an application of IoT in the shopping sector, e-commerce sector, which is actually called smart shelves. Now, IoT in healthcare, there is no need to mention about this particular domain. So IoT is highly useful in patient monitoring, especially people who are in the in the ventilators or in the ICU. Their health conditions can be monitored using sensors or using the IoT devices, and it can give alarm, or it can give messages to the doctor or the nurses, the medical personnel, regarding the health condition of the patient who is currently in the ICU or in the ventilator. So these IoT devices are highly used in patients' health monitoring, already there in the health sector. Then tracking the location of a medical equipment. You want a wheelchair, or you want some device immediately, where exactly it is, that can be sensed or that can be tracked immediately using these IoT devices. Then ambulance services. When an ambulance is coming on the road, ambulance should reach the hospital at the earliest. So there are devices or there are IoT enabled ambulances which will give signal or which will give information to the traffic signal or traffic post that there is an ambulance coming, so that it will not immediately change green for other devices, but it will wait, it will remain as red, so that other vehicles are waiting and only the ambulance goes through the traffic signal or crosses the traffic signal. So there are already smart devices, and in the health sector, for tracking devices, for tracking people, for monitoring patients, ambulance, etc., IoT is highly used. And another domain where you find application of IoT today is actually the food security and in the agricultural field. All of you might have heard about precision farming. So this is actually a research area in which Microsoft is focusing. Microsoft research is coming, or they are actually giving very much importance for agriculture, and they have a research team or this research wing, MSR. Microsoft Research is working on precision farming. How precisely we can do the farming when you have a large farm, how we can how much water is required for a particular plant. We should not pour more water, or there should not be any particular plant which is having less water. So how can we go for precision farming is actually a research area of Microsoft Research. So there they are highly making use of drones and the sensing devices, and it is actually an area which is coming out of IoT. So live tracking of the weather and the environment, that is one sector where you find a lot of applications of IoT. Selection and harvesting crops, which is the best crop which we should harvest in the coming season. Then monitoring the crop health, as I said, using drones and IoT enabled devices, you can monitor the health of each and every plant in the farm. So monitoring soil nutrition level and water content. So these are all some of the areas where people have already deployed and found IoT enabled applications very much successful. So driverless cars, it is no longer a dream. You know that the driverless cars are already there. It is already existing. So people are talking about automated driving. So people, in today's busy world, nobody wants to spend his whole energy on driving your car. In a city like Kolkata, where there is heavy traffic, when you start from your home and when you drive up to your office, you will be highly tired because of the traffic. And when you reach the office or when you reach the department, you will not have that much energy to take class on that particular day. So think of a situation where you are sitting in the back seat of the car and the car drives automatically and takes you to your college or to the university. And you sit back, you sit and just prepare for the classes or just go through the assignments that the students have submitted, or just go through the things that you have to deliver on that day. That is actually possible in these driverless cars or smart cars. That is actually a reality now. So the smart cars or driverless cars are highly dependent on this IoT technology or Internet of Things. So everything this is actually an example. So here the gear system, the steering, Wi-Fi, all the things are inside the car, and the total coding that you may require for making a smart car or a driverless car, if you look in terms of the code, that may be much higher than the code that you have to write for developing an operating system. So the Microsoft operating system, or when you talk about the Linux OS, you can imagine how much code or how many lines of code, LOC, is there in the OS source code. Much more than that is required when you write the code or when you develop the software for a smart car or for a driverless car. So it is actually a reality. I mean, we in India also, or in our Asian countries also, we hope soon these driverless cars will become very popular. So it is actually a very hot area in IoT. Lot of people are funding or they are doing research in driverless cars. So it is also, I mean, an offshoot, or it is a hot area in the IoT research. So tracking applications, preventing accidents. So you have to keep distance from other cars. So you have to sense the how far the car which is going ahead of your car. Accordingly, you have to reduce or you have to increase the speed, and ultimately the vehicles need to be smart. So smart vehicles is a very hot area in IoT research. Okay, so there are a lot of misconceptions about IoT. What IoT represents is still not clear among some of the researchers. It is common to equate the entire IoT paradigm with any one of its building blocks. So this is actually the confusion. People are getting confused with the building blocks of IoT, and they think that is actually the IoT. So what are the building blocks of IoT? These three things: embedded systems, networking, cloud computing, and data analytics. These three are the building blocks of IoT. These building blocks are often referred to as IoT enabling technologies. So the IoT enabling technologies are confused as IoT itself by the people. So what are the three IoT enabling technologies? Embedded systems, networking, and cloud computing and data analytics. So in that sense, radio frequency identification, RFID, wireless sensor networks, WSNs, etc. form only the building blocks of IoT. So when you search for a research article in IoT, you may get some papers which are on wireless sensor network. So, or you will get some papers on mobile ad hoc networks. So you may think ultimately that this IoT, wireless sensor network, and RFID network are all the same. They are all not the same. But please note this particular point that embedded systems, networking, cloud computing, data analytics, WSN are all different IoT enabling technologies. They are not IoT itself. But people confuse and they think that wireless sensor network is same as IoT. It is not like that. Now I hand over the session to my student Sri Jay Suraj, who is actually working in this particular area. So he is actually working on a specific topic in IoT, which is actually called low power lossy networks. So I am handing over and I am requesting Jay Suraj to take forward from here. So he is connecting from Trivandrum, the capital of Kerala. So over to Jay Suraj. Jay Suraj?
Yes. Thank you, sir.
Yeah, Jay Suraj.
Am I audible?
Yes, you are audible.
Am I audible, sir? Okay, thank
Yes.
you, sir. And thank you all for this opportunity.
Yeah, I will stop sharing. Yeah, you can share your slide, Jay Suraj.
Okay, sir. So, are the slides visible to all?
Yes, it is coming.
Okay, so let me begin let me continue from where you have stopped, sir.
Just a minute, Jay Suraj. Yeah, it has come. The slides have come.
Okay, so currently the slide is layers in the IoT paradigm.
Yes. Players in the IoT paradigm.
Oh, okay, sir. Thank you. So, good afternoon, all. Now, I am actually taking forward the slide from what Madhukuma sir has already told. Now, till this point of time, you have seen a lot lot of technologies or lot of applications of the IoT. And also, sir has explicitly mentioned that these applications can be realized only as a result of a combination of multiple technologies and not a single technology. And also, you have seen that there are three enabling technologies: embedded systems, networking, and cloud computing and data analytics. So, regarding these technologies, actually, these technologies are grouped into three layers. That is layer one, that is the base layer. In the figure, the bottommost layer, that is the sensing layer. This is the layer where the things are connected. Things attached with sensors are connected. That is the layer. That is the sensing layer. That is the basic layer and the layer one. So this corresponds to the sensing of. You have seen that sensing plus communication plus computing defines an IoT paradigm. So this layer defines sensing, the sensing layer or the perception layer. And then the layer on top of that, that is the layer 2, is the network layer. In the case of network layer, it handles the IP-enabled communication of the things. That is, this is a layer which is responsible for adding the things to the global internet. That is network layer. So this corresponds to communication in the definition of IoT paradigm. And finally, the topmost layer is the application layer. Here is the place where the large amounts of data sensed are analyzed using technologies like cloud computing or fog computing and all. So this is the layer which is in contact with the user, and this specifies the computing aspect of IoT. So these are the three layers. More details regarding the layers we can see later. So this represents a more detailed representation. It is the same as that of the previous figure. It just provides an expanded vision. For example, the first two layers will be the second will be the sensing layer. Then the next two will be the network layer, and the last two will be the application. It is same, but in a more generic way. So evolution of IoT. It won't go overboard if we say that IoT keeps on evolving. That we all know, because IoT is a paradigm which is always evolving. It is evolving currently, and there is no idea how much extent it will evolve in the future. It is always keeps on evolving. So for that, we can say that IoT architecture itself can be considered for its evolution. So the justification of this point can be understood from this figure. That means, in the earlier stages, the sensing layer or the layer 1 alone was there. That is, things were able to communicate, but they were not connected to the internet. So that marks the level 1 of evolution. When it was connected to the internet, network layer was to be added. That marks the second generation. And once it has become part of the internet, massive amounts of data began to be generated, and hence application layer also came. So we can surely say that IoT architecture itself can be considered as proof for its evolution. So from machine to machine communication, that means communication without internet, it has come a long forward with its incorporation in the global internet arena. So this is a brief sketch of the evolution of IoT. Now we can see, with the basic knowledge of the IoT concepts, we can now see what is the architecture of Internet of Things paradigm. As already mentioned, we have seen what is the sensing layer. So what is the importance of sensing layer? That is what is given in the first point. This layer is important considering the fact that things which denotes the characterizing feature of IoT reside. That these things are residing in the sensing layer, because without sensors, IoT is not unique. It will be like any other network. What makes IoT unique is the presence of things, everyday things, attached with sensors or actuators. So that is present in the sensing layer. That is why it is highly important. It acts as the base for any IoT application and all the higher layers. Now, things are attached with sensors or actuators or both, unlike the standalone wireless sensor networks. As Madhukumar sir has already said, there is a confusion regarding what is wireless sensor network and what is Internet of Things, or what role it has in Internet of Things. Wireless sensor network is actually a network of sensors. It is mainly used for data collection, or for collecting the sensed information in a sync node. Actuators need not be present in wireless sensor network, but in the case of Internet of Things, actuators should be present. Why? Because only with the presence of actuators, things can perform an action. If only sensors are present, things can only sense. It cannot do any response, or it cannot respond with any action. So for that, actuators should be present in the case of Internet of Things networks. So some of the networks are RFID networks, wireless sensor networks, low power and lossy networks. All these kinds of networks comes under the sensing or the perception layer. Now we can see the earliest form of the sensing or perception layer, that is the radio frequency identification or the RFID. You all may be familiar with RFID tags. So it can be said as the founding technology for the IoT paradigm. It was the first phase of evolution. Thus, here the idea was to use the RFID tags in accordance with the electronic product code. A global item identification represented by this electronic product code was assigned to each physical object. So what is the usage of tags? The tag will contain, or the RFID tag will contain all the information corresponding to a particular commodity. So when a tag is attached to a commodity, that tag electronically stores all the information with or corresponding to that commodity. There may be an equivalence with the barcode which we are seeing now. So this was the earliest form. So these identifiers were stored in tags directly attached to the objects, identifiers for the objects. So this is one of the example figures of how an RFID tag looks like. All the RFID tags may not look like this, it is just an example. Now the next phase is wireless sensor networks. Even though RFID was the first phase of evolution, wireless sensor networks is actually the more popular version of technology used in the Internet of Things paradigm. So this is the next important step in the evolution of IoT. As I have already said, traditional wireless sensor networks contains only sensors. Therefore, they were designed primarily for data acquisition. But in the case of IoT, wireless sensor networks contains actuators along with sensors. Therefore, they are often referred to as wireless sensor and actuator networks, or WSAN. Need not be. Sometimes wireless sensor network directly implies that sensor and actuators are present. Therefore, you might not come across this term of wireless sensor and actuator networks in a frequent manner. But when you see wireless sensor network in the context of IoT, it actually means wireless sensor and actuator networks. So at this point of time, there were RFID objects as well as sensor nodes in the wireless sensor network. That is why attempts were made by the researchers to integrate RFID as well as wireless sensor network based on the EPC framework. So this was necessary. Why? Because some things or some everyday things or commodities were having RFID tags, whereas some others were having sensors. So these two, whether they are having RFID tag or sensor, they are everyday things and they should communicate with each other. Therefore, integration of these two should have been mandatory. So that kind of attempts were made by the researchers in the early stages. Now, we can see how the integration of RFIDs and the wireless sensor network with the internet took place. We have seen that in the second phase or in the second layer, that is the network layer, all the things are connected to the global internet. The things are not simply communicating with each other, they are actually connected to the global internet arena itself. So how we can see how integration of RFIDs and wireless sensor networks with the global internet took place. So for that, there are two options. There were two options considered. One is integration at the object level and integration at the system level. First, when we consider integration at the object level, in the integration of object level, the solutions considering the resulting node consider the resulting nodes as either RFID tags equipped with sensors or as wireless sensor nodes with a unique ID. That means in the under integration at object level, there were two alternatives considered. One is RFID tags were equipped with sensors. So ideally, it is an RFID network, but RFID tags will be equipped with sensors. That is what happened in the first solution. But in the second solution, there is another alternative. There is no RFID, but only wireless sensor nodes with a unique ID. So can you guess which among these two will be or prove to be more advantageous? It is the second one. First option of using RFID tags equipped with sensors had a lot of disadvantages because that method, that is the former method, that is usage of RFID tags equipped with sensors, has the disadvantage of not being able to support direct communication between the nodes. Direct communication between the nodes means device-to-device communication or point-to-point communication, direct communication. Such kind of communication was not possible. Do you know why? It is because RFID tags cannot work alone. There should be an RFID reader. You have always seen that there is a barcode and barcode reader, right? Similarly, there is RFID tag as well as RFID readers. So, direct communication between one RFID tag to another RFID tag is not possible. If an RFID reader should always be present. So, such kind of disadvantages were there in the first option. Now, the second method has the advantage of using wireless multi-hop communication procedure. That is the usual wireless routing procedure. So this was considered more advantageous compared to the first one. Now, integration at the system level. So for the time being, you please understand that it uses a gateway at the edge of the network infrastructure. We can see it using a figure. So this provides the figure of how integration at the system level took place. Integration at the system level means here there is what you can see, there is a wireless sensor network. That is a network of sensor nodes. Here there are a lot of RFID tags, and each RFID tag has to be connected to a reader, RFID reader. That I have already said in the previous slide. So through the reader, they can communicate to the global infrastructure. But in the case of wireless sensor network, they use a gateway. A gateway device will provide the to the global internet format, and then they will go to the global network infrastructure. So this is a brief overview of what system level integration took place. No need to say this is the popular method. This emerged to be the popular method, and this is what is being considered, although in a different form. So now we have seen what is sensing layer. Now we move on to network layer. Network layer operates in the core network, which is responsible for providing IP connectivity. That means it operates in the global internet platform. And this is the layer which gives IP addresses to the things or sensing devices or IP connectivity. Only with this, we can say that things are connected to the internet. Otherwise, it is only network of things. Network layer allows the transformation from network of things to internet of things, because network of things does not use global internet. Internet of things, on the other hand, uses the global internet architecture, and they are responsible for providing the IP connectivity. So here the focus is on enabling things to get directly connected to the internet like any other host. We know that in the traditional internet, a lot of devices are there. Our laptops, mobile phones are all there. They are having IP connectivity. Similarly, all the everyday things are also assigned IP addresses so that it can get connected to the internet. Now, the organization which made this possible was the Internet Engineering Task Force. For your information, please note that Internet Engineering Task Force has created a lot of working groups in order to address a lot of issues with the Internet of Things. You may even note that some of the working groups like ROLL, ROLL, have done a very valuable work regarding routing in Internet of Things. So that is what an introduction about network here. In the next phase, we have to see what is 6LoWPAN. 6LoWPAN, as noted in the first point, it finds its expansion as IPv6 or low power wireless personal area networks. That is what 6LoWPAN stands for. So from this abbreviation itself, it is clear that it is a lightweight version of the IPv6 protocol. So why this lightweight version of IPv6 protocol was required? That is because things present in the Internet of Things paradigm are not similar in capacity with the traditional Internet devices. The things are always resource constrained in nature. Therefore, each and every protocol we employ on the thing should be lightweight in nature. So that must have prompted the researchers to develop a lightweight version of the IPv6 protocol, which is known as 6LoWPAN. Now, sensors in IoT, which are highly resource constrained, uses different protocols like ZigBee, PLC, RFID, etc. So this also is different from the standard Internet devices. We know that standard protocol is TCP/IP, normal devices, but that cannot, or that kind of uniformity cannot be said for Internet of Things devices. They will use different protocols. Some will use ZigBee, some will use PLC, some will use RFID. So all these protocols will be there. So what will happen is there should be an interoperability among these different protocols. 6LoWPAN provides exactly that. So in that case, 6LoWPAN is relevant. But that alone is not the relevance. There are other relevances also. 6LoWPAN performs the header compression required to suit the resource constrained IoT devices. I have already said that things are resource constrained in nature. Therefore, IPv6 packet should be simplified. So this performs the header compression in order to simplify that. To be more specific, we can say that the header compression is performed between the data link layer and the network layer. So 6LoWPAN performs that header compression. Now, through the usage of gateways, 6LoWPAN packets can be converted into standard IPv6 packets. Now, so why this conversion is necessary? Because 6LoWPAN is applicable only in the networks of things. We know that the networks of things should be ultimately connected to the global internet, isn't it? Then only it will become Internet of Things. Therefore, through the usage of gateways, the 6LoWPAN packet can be connected or converted to the standard IPv6 packet suitable for use in the global internet. So we can say that in the individual networks of sensors or things, 6LoWPAN packets will be exchanged, and at the gateway to the global internet, it will be translated to the standard IPv6 packet. Now, another important function of 6LoWPAN is that 6LoWPAN also facilitates the transformation of each device into a web server. That also we are familiar. There is a World Wide Web in the internet that we are all familiar. All the objects of the servers are having corresponding web counterparts also. So when we are talking about integrating things to the global internet, just physical integration to the internet is not sufficient. We have to do a web level integration also. That assistance also is provided to some extent by the 6LoWPAN standard. Having said that, now we can see Web of Things. Till now we have seen Network of Things, Internet of Things. Now what is Web of Things? Web of Things means integration of sensor nodes into the internet requires the support of HTTP-based services. HTTP we are all familiar, but that is for traditional internet devices. For merging the things with the World Wide Web, there should be an equivalent protocol like HTTP. So in the Web of Things, sensors are modeled as web services which are uniquely identified by a universal resource identifier. This is same as that of any other internet resource. We know that any internet resource in the web is identified by a universal resource identifier or URI. And then get and set methods are used. This is also same as in the case of all web pages. So you can guess actually what get and set methods signify in the context of Internet of Things. Get means in order to get means in order to extract some sensed information from the sensor. Set means in order to add some of the constraints or properties to the sensor. So similarly, get and set methods are used as in the case of all web pages. So in the previous slide, I have already said that a need for HTTP-based protocol is there. So that kind of protocol which is used in the area of Internet of Things is Constrained Application Protocol or CoAP. CoAP, like 6LoWPAN, it is characterized by simplicity, low overhead, and support for multicast communications. These are all necessary in the case of Internet of Things domain. Now, CoAP is usually executed over UDP, or User Datagram Protocol, so as to obtain lower overhead. This is different from HTTP. HTTP is usually run over TCP, although it can also run over UDP. Commonly, it runs over TCP, but CoAP is usually executed over UDP. Why? Because in order to obtain lower overheads, so it is always executed over UDP. Now, similar to 6LoWPAN, this CoAP also requires a translation. So it can be easily translated into HTTP through the usage of appropriate gateways. Again, please remember that CoAP is suited for things, and things are ultimately getting connected to the internet. Therefore, a translation from the things level protocol to the global internet protocol is necessary. Again, that is facilitated using the usage of or through the usage of gateways. Now, there is another concept in the layer 2, or that is the social networking. Social networking, we all know, we all have Facebook accounts or different social media accounts are there for almost every one of us. So how about thinking a scenario where the things are also having or are also becoming a part of the social networking? What will happen? That is the idea behind the IoT application of in social networking. It allows the owners to share data generated by the smart objects with people they know. We know that different settings, right? In the case of Facebook, we can set the visibility regarding who all can see the post shared by our friends. Such kind of visibility settings we can do. Similarly, we can also provide visibility settings to the object, to our objects, who all can see, whether all of our friends can see, or only some section of the friends can see, or all the public can see. Such kind of things can be realized in the case of IoT in social networking. So for this, as I said, there are different implementations. For example, limited visibility. For example, social farm project. Here, only limited visibility is needed. There is no need for a vast amount of visibility. If increased visibility is given in such critical applications, there is a risk of hacking always. Now, there are applications where it is visible to a group of people or a community, and there are applications where it is visible to a large amount of people. That is benchmarking. Benchmarking is done to compare the performance of a person or a community with respect to a larger set. That is what benchmarking is. So suppose I am going to evaluate my performance. I can evaluate my performance only when I know the performance score of all the related persons. So in such cases, more visibility is needed. So what I was trying to say is social networking allows us, the owners, to set visibility to data generated by the smart objects. Having said that, now we can say what is application layer. In the first figure itself, we have seen that the base layer is sensing layer, on top of it is network layer, and the topmost layer is application layer. This layer is concerned with the enormous amounts of data that needs to be stored and analyzed. We have seen that a lot of things are getting connected. In the introduction slide, Madhukumar sir had already said that by the year 2022, the number of IP-enabled devices is likely to reach 4 times the existing population at that time. So enormous amounts of data will be generated, and these amounts of data should be analyzed and stored. That is concerned with application layer. So how will it be done? We will have to use the services provided by cloud computing as well as big data analytics. So these two are the technologies which are of predominant usage in the application layer. The large amounts of data generated are sent to the cloud where functionalities like encryption, authentication, and duplication can be performed easily. So all these applications or all these operations are highly mandatory in the case of IoT, because you just can imagine what is the need of encryption, because IoT is playing with the private data. Aspects should be there. These things can be performed in the cloud, and then cloud also helps in managing heterogeneity by providing a common IoT application development layer where different devices are virtualized. So virtualization is a common known application of cloud. So different devices can be virtualized in cloud, and then heterogeneity can be addressed. At this point, we should remember that the IoT devices are highly heterogeneous in nature, based on protocols, based on its characteristics, based on its utility. They are heterogeneous in different ways. So this kind of heterogeneity can be addressed in cloud, where these devices can be virtualized. Now, services from different providers can be merged so as to provide complex services. We can say that Internet of Things is concerned with the global internet. Therefore, there will be different providers, not just a single one. If a platform like cloud is there, services from different providers can be efficiently merged so as to provide more complex services and more useful. Complex means it's not, you should not think that it is computationally complex services. It is like providing more advanced services by merging different services from different providers. Okay, now we have seen the different layers in the IoT architecture. With that knowledge, we can now see what are all the scope for further research in the field of Internet of Things. As more and more things are getting connected to the internet, potential application domains of IoT are also increasing. That means we all know that Internet of Things is concerned with attaching everyday things to the internet. Now, actually, is there any limit to how many things can get connected in the future? There is no limit. More and more things are getting connected in an increasingly fast manner. Therefore, when more things are getting connected, consequently, the application domains of IoT are also increasing. We can address all these applications. But we know that the application layer is the topmost layer. It has two basic layers or base layers. The most basic layer, sensing layer, and the top of that or the middle layer, that is the network layer. So the sensing and network layers also need to be enhanced because it is actually a layered paradigm. We are all aware of a layered paradigm. For example, ISO OSI model or TCP/IP model, they are all layered paradigms. That means layer on top is supported by the layer just beneath it. So when we are going to develop highly developed applications, we should make sure that the underlying sensing and network layers are equipped to meet the conditions of that application. So we can say that this offers several research opportunities in all the three layers. The sensing layer, there are opportunities. Network layer, there are opportunities. And in the application layer, there are opportunities. This is because IoT is still evolving. If IoT had reached a particular level of evolution, sometimes more amount of research will be conducted on the application layer. But since it is a still evolving paradigm, sensing layer, network layer, and application layer, all these things should be addressed. So we can surely say that this offers several research opportunities. Now we can see the road ahead of Internet of Things. We as researchers have a lot to research, a lot to contribute in the area of Internet of Things. There are a wide variety of research challenges that can be seen in this section, IoT Internet of Things road ahead. First challenge, integration of resource-constrained networks. In this aspect, a particular terminology comes important, that is low power and lossy networks, which is usually abbreviated as LLNs. These are characterized by the highly resource-constrained nature because these networks contains essentially things alone. It does not contain the traditional internet or network devices. Low power and lossy networks contains the things alone. We can surely say that in terms of resource constrained nature, it is even more critical than the wireless sensor network. Wireless sensor network is highly limited in resources, but low power lossy networks are even limited. So in the research in low power lossy networks is actually given a lot of attention by the Internet Engineering Task Force, which has set up a lot of working groups in order to address issues in low power and lossy networks. Now, not just low power and lossy networks, wireless mesh networks, smart vehicles, body area sensor networks, flying ad hoc networks, all these kinds of networks can be integrated. We know that these are all standalone networks. These old networks have an existence of its own, even without internet connection. But when we connect these networks to the internet, it will surely become a part of the Internet of Things, and this can be useful in realizing a lot of socially relevant applications. So not only these much, many other standalone networks can get integrated. Now, once we have said that these can be integrated, there are some challenges in integration. Four main challenges are listed here. One is bidirectional traffic. This challenge essentially means the fact that these standalone networks are connected to the internet through a gateway. So what is the natural consequence? There will be traffic from these standalone networks to the internet, as well as there will be traffic from the internet to these standalone networks. There is traffic in the upward direction as well as in the downward direction. So, or in more technical terms, we can say that there is bidirectional traffic involving both uplink and downlink traffic. So when we are integrating any of these networks, this issue should be considered. We should be able to route the data packets in both the directions. So this should be considered. The next is mobility. The second point. Second point is mobility. Mobility comes into relevance when we consider the fact that industrial IoT has become more popular now. Industrial IoT requires things to be moving in some situations. For example, things may be moving on its own, or the things may be on a moving object or a moving entity. Maybe things will be present in the pocket of a human being or may be present in a vehicle. In any case, mobility needs to be addressed. In that case, opportunistic networking can prove beneficial because opportunistic networking is concerned with maintaining continuous connectivity. It cannot be continuously connected to a single point, but it has to be ensured that the mobile nodes are connected to some static node at all points of time. We cannot ensure that all the mobile nodes should be connected to a single static point. It's not like that. It should be connected to some static internet infrastructure. That should be considered. Then the third one is multicasting. multicasting has a huge relevance in Internet of Things paradigm because several applications, even including smart street lighting, multicasting should be there. In the case of smart street lighting, it's actually a basic and simple example. Here, a group of street lights should get automatically switched on and switched off. So multicasting should be there. In that case, we have to say that this field is not developed in the case of Internet of Things. In the case of Internet of Things, usually multiple unicasting is performed. Multiple unicasting means first we perform a unicast, then again a unicast, and similarly, you will have to perform a lot of operations. It will result in a very much increase in overhead as well as end-to-end delay. So multicasting should be considered. And finally, single point failure. So what is single point failure? We have already seen that all these standalone networks are connected to the internet through a gateway. So essentially all the traffic from these resource constrained networks will have to eventually pass through the gateway in order to reach the internet. So there is a high chance that a lot of traffic increase can happen in areas surrounding the gateway. So this can result in failures. So these are some of the issues which we as researchers should consider while integrating different standalone networks with Internet of Things. Now this is another possibility, that is information-centric networking. Information-centric networking, which is usually abbreviated as ICN, matches with the content-specific nature of IoT applications. So we are actually familiar with IP-enabled networking, right? We are setting up routes are established, and then information is transmitted. But in the case of information-centric networking, routing is not taking place like that. It is based on the content to be received. It is not like first route is set up and then content is transmitted. It is initially inquiring for the content. So it is content specific, and this content specific nature of information centric networking matches with the IoT applications because, as already said, IoT is highly application specific and a lot of content gets generated. So if somehow information centric networking can get integrated with the IoT paradigm, it can result in a lot of beneficial changes. Now, another benefit is that in-network caching is possible with ICN. Information-centric networking provides in-network caching, that is, content can be stored within the network itself because routing anyway is done based on content. So this can be done in the network layer or the routing phase itself, the caching can be performed. So this can result in saving a lot of time, and in fact it also reduces the control overhead. And the third one, naming flexibility in ICN can improve the scalability. We know that there was a condition that IPv6 was discovered after IPv4. That means when more number of devices get connected to the internet, we should have addresses to assign to them. So in IP-enabled networking, address assigning is of utmost importance. But in the case of ICN, there is no IP. They are identified by the ID. Therefore, naming flexibility is there. It can improve the scalability. Then another feature is that ICN improves security by securing the content itself instead of the communication channel. We are always aware of the usual security procedures. First, a channel is set up, and then that channel is secured. There can be third party for signature and security certificates and all. These kinds of things can be avoided because here actually content is directly routed without creating any route. So it can secure the content itself instead of securing the communication channel. It can directly secure the content. Now the last point, the receiver-driven nature of ICN supports mobility to a large extent. So what is this receiver-driven nature? In proper network routing, what is the procedure? A sender node will send a packet to the receiver. There, the receivers are not actually asking for a particular content. Sender is sending a particular information to the receiver. But in the case of information-centric networking, it is receiver-driven. The receiver says, I want that content. It is not sender-driven. So receiver-driven nature can support mobility because usually the mobile nodes are the receivers. They are not part of the static internet infrastructure. So since they are the receivers, the receiver-driven nature of ICN can support the connectivity, intermittent connectivity of these mobile nodes to a large extent. So these are some of the things which can be considered while integrating information-centric networking with IoT. This actually has a lot of scope for research in the future. Now, interoperability issues. Interoperability issues, there are mainly 2 points. The first one, the application served by the IoT spans a wide range. We have seen that there are transportation applications, there is healthcare application, there is agriculture application, there is shopping application. Different applications are there, and each application has its own quality of service requirements. So what is quality of service? Quality of service means how well a particular application is served. That is quality of service. So each of these applications will have its own quality of service requirement. For example, healthcare quality of service will not be the same as that of transportation. That will not be the same as that of agriculture. So each application is highly different and unique in nature with respect to other applications. Now we can explain this based on a figure. So here this figure shows horizontal and vertical integration. In this case, you can see a lot of horizontal columns as well as vertical columns. Suppose in this thing, in vertical, it is service sectors. Sorry, it is energy. It is in this vertical aspect, it is consumer and home. In this vertical aspect, it is all healthcare. This is industrial. So all these vertical aspects, or we can say silo, these vertical silo represent a unique application of the IoT. Consumer, healthcare, and all these will have different requirements. Now consider the horizontal. So here, this is healthcare, this is another aspect of healthcare, and this is another aspect of healthcare. This is industrial, this is another aspect of industrial, and this is another aspect of industrial. So the horizontal section signify different aspects of the same application. So we have to understand that integration should happen in the both vertical as well as horizontal level. Then only IoT applications can be realized. For example, you can consider the smart city. Smart city means city contains homes, hospitals, shopping complexes, all these things, and all these things are having different requirements and different technologies. These should be efficiently combined and integrated. Then only interoperability can be achieved. Only if the interoperability is achieved, efficient or complete realization of Internet of Things is possible. Now we can see yet another important area. This area called Social Internet of Things, often abbreviated as SIoT, might draw a significant research attention in the near future itself. As more introduction regarding this has been provided in that social networking slide, you can say that SIoT allows objects to create their own social network separated from that of human beings. You can just imagine, we are having social media pages. Suppose things are also having social media pages. What will happen? This is shown in this figure actually. In this figure, this is represented as a thing. This is a thing. This is a man. We. This is again a thing. So in this internet or social networking, things are present. Human beings are present, and all are having the same privileges. Like human beings, things can also take part in social networks. They can create groups. They can create friend circles. They can cooperate with that community to provide a service. So this is a very interesting idea which is put forward by the researchers, but mainly till now it exists in theory. There may be some implementation, preliminary implementation regarding social Internet of Things. It predominantly exists in theory. Therefore, we can surely say that research is required regarding how to implement the needed architecture and protocols for realizing social Internet of Things. This is an area which might draw huge research attention in the near future. Now, two technologies which we cannot omit are fog and edge computing. We are familiar with cloud computing, but what is fog and edge computing? Fog and edge computing are rapidly getting along with cloud computing techniques. Since IoT involves generation and processing of large amounts of private data, security risk is always there. So what is a public cloud? Public cloud means it is a part of the internet. So we are having the risk of exposing our large amounts of private data into the public domain. That needs to be reduced, otherwise security risk is always there. So fog computing and edge computing were proposed. Regarding fog computing, it makes use of local storage as well as cloud data centers. That means it uses local devices without going to the public platform. Only if it is highly mandatory that it should go to the internet, it will be sent to the cloud data centers. The concept is that this data is not always sent to the public cloud. Instead, if possible, it is analyzed in the local storage itself. That is fog computing. Now the next is edge computing. Edge computing means it restricts all the information in the local part itself. There is no switching from between the local and cloud. Keeps all the information in the local part. So you can naturally infer that edge computing is even more secure when compared to fog computing. So these are some of the benefits of fog and edge computing. Regarding fog computing, as you can already infer, low latency. Why? Because internet connection is not always needed, because there are provisions to perform the analytics within the local storage itself. Then better data control. Once the data is sent to the public domain, we are not having that much control. But if it is restricted to the local storage, as in the case of fog, better data control can be ensured, and the storage system is flexible. It does not ensure that, or it does not strictly say that it should be performed in cloud or it should be performed in local storage. It can be performed in either as per the requirement. Now, benefits of edge computing, there is actually no delay because there is not at all internet required. All the analysis and storage are performed in the local storage itself. So real-time data analysis is possible. Network traffic can be reduced because huge traffic will not get generated to the internet, because much of the information are being processed in the local centers. So and also it results in reduced operating costs. These are some of the benefits, and these two technologies will have a role to play in the future of Internet of Things. Especially current research is more focused on edge computing, how to integrate edge computing in Internet of Things. There is a common news that networking moves to the edge. So this is an area which has a lot of research attention and relevance at present. Now we come to the ending slides. So here we can address the terminology known as Internet of Everything. I have included this slide because this is actually a confusing terminology. What is Internet? What is Internet of Things? And what is Internet of Everything? Are they same or are they different? We can say that Internet of Everything is actually IoT itself, but in a broader view. That is because when we hear Internet of Things, we will say that things are communicating with each other using internet. But actually the internet contains all the traditional devices. Those devices are not going anywhere. They are always present. Therefore, actually IoT uses internet, which in turn hosts a lot of traditional internet devices. So we can say, or more correctly term it as Internet of Everything. So IoT allows things to be part of global internet arena, which in turn already has traditional internet devices. That is what I have just said, along with human beings as the end users. So when we hear Internet of Things, we will assume that things are the end users. But Internet of Everything means there are things as end users as well as we human beings are also there as end users. So this provides a broader view. Now another terminology is Internet of Vehicles. Internet of Vehicles is another term which is used to represent the inclusion of vehicles into the internet platform. Similar to things, vehicles are integrated, that's all. Then there is Internet of Drones. It includes flying objects like drones into the internet. These are all actually things only. Vehicles and drones are all smart things. So we can always club IOV or IOD with IoT itself. We can identify both IOV and IoT with IoT. Even though there is nothing wrong with IOV and IoT terms, in order to avoid the confusion only, I am saying IOV or IoT, either we can actually equate it with IoT, and IoE presents its more broader view. So these are all different terminologies eventually pointing to either IoT or IoE. Now let us conclude. We have seen that Internet of Things is the result of a constructive fusion of technologies like embedded systems, networking, cloud computing, and data analytics. This should be the main takeaway, because we should not make the mistake of equating IoT with any of its component technology. All the technologies have its own important roles to play. Only when they play their roles in the most efficient manner, the complete realization of Internet of Things is possible. So that is the main takeaway actually. It's forced to entirely equate IoT with either of its component technologies. It is still an evolving paradigm which offers a spectrum of opportunities for researchers. We have seen a lot of opportunities are there in all the three layers, be it sensing layer, network layer, or application layer. All layers provide a lot of opportunities for the researchers. For example, we have seen the integration of standalone networks. That is an opportunity. ICN or information centric networking is yet another opportunity. Social Internet of Things that we can efficiently utilize. Then fog computing and edge computing that can be efficiently integrated. Similarly, a lot of opportunities are being provided by the Internet of Things. So we can say that a complete realization of IoT is highly recommended considering various socially relevant applications it can fulfill. That means in order to develop all the potential socially relevant applications of IoT, the base should be strong. We can perform research in the base. There is huge scope, and also we can parallelly develop socially relevant applications. So we can say that IoT offers a lot of possibilities for researchers. Now we can see some of the components required for IoT experimentation, or components which are required for setting up IoT labs. This is only a preliminary list. This is not a list for full-fledged IoT lab. It is only a small list for basic setup of IoT lab. One, we should always know, we are always familiar that sensor modules should be there. Different kinds of sensors should be there. And such modules are available where multiple sensors are embedded. A single module will be there, but multiple sensors will be embedded. Such kind of modules are available. Then data acquisition cards are there. That means the sensor should sense the information, therefore, or sense or gather the information. So that data acquisition card should be there. Then modes should be there. So what is a mode? Mode means we have already seen that in the case of IoT, actuators are present. Sensors and actuators are present. So these sensors as well as actuators with the functionality of a transceiver. Transceiver means capacity to transmit as well as receive. So such objects or components are referred to as modes. That is needed. Then multi-protocol gateways are needed. That again we have seen. There are a lot of protocol translations taking place in the Internet of Things. While the sensed information is going to the global internet, heavy translations are required. For example, 6LoWPAN should be translated to IPv6. CoAP should be translated to HTTP. So multi-protocol gateways should be an integral part of any IoT lab, be it basic or advanced. Now these modules, actually it is available in the market, or in fact in CDAC, they are providing with these kits for setting up basic IoT labs. Now simulators are actually needed because networking, as we have seen, is an integral component. In fact, it is the basic layer. In the sensing layer and network layer, the major operation is networking. So in that case, we will have to rely somehow on the simulators, because otherwise it is hard to correct that many number of sensor modules. Therefore, for advanced experimentation, it is always desirable to have simulators, especially for network related protocols. So the main simulators are Contiki Kuja. So this is the main simulator. Even it surpasses NS2 or NS3 in the case of IoT, because these simulators comes with an inbuilt Contiki operating system. This Contiki operating system is the popular operating system along with Tiny operating system. This Contiki and Tiny operating system are the operating systems which are used by the things. Therefore, Kuja can be said as more accurate simulator in the case of simulating IoT, and also many IoT protocols have been included in the Kuja library. So that is an important simulator. Then there is NetSim provided by the TechCos. NetSim is important regarding the easiness in coding. It is actually a highly advanced simulator that is almost a drag and drop kind of thing. We can save a lot of time with NetSim, using NetSim. But the problem is that unlike Kuja, NetSim is not really available. We have to pay for it. But Kuja is an open software. Now NetSim, it can also be used as an emulator, not as simulator, but not alone as simulator, but also as emulator. So these are some of the components which can be used for setting up a basic IoT lab. Now, for the researchers, it might be useful to know some of the important conferences and journals in the area of IoT. Regarding conferences, there is a conference in the name Internet of Things itself, International Conference on the Internet of Things. I think the 10th edition is happening in 2020. So this is a conference of ACM. So this is an important conference. Then there is an Indian conference. This conference we all will be familiar. International Conference on Communication Systems and Networks, or COMSNET. It is usually conducted in Bangalore, and it is coordinated by IISc as well as the IITs along with industries. So this is a really good conference where we can find standard papers for wireless networks, and IoT, or Internet of Things. Then regarding journals, IEEE provides an Internet of Things journal. So this journal we can use for understanding the various or the latest innovations in the field of IoT. That is a good journal. Then from Elsevier, Future Generation Computer Systems, it provides a lot of papers regarding the application layer of Internet of Things. Even though sensing and network layer are also included, in order to get papers on the higher levels, Future Generation Computer Systems Journal of Elsevier can be used. Now, these are some of the online courses which the interested researchers can do. Both incidentally are titled the same, Introduction to Internet of Things. The first is coordinated by the IIT Kharagpur, and it is available in NPTEL as well as the SWAYAM platform of the central government. And the second one is provided by the Stanford School of Engineering. And these things we can access by merely searching in Google. These are available. So these are the references. Thank you. And if you have any questions, you may please ask.
Thank you, Mr. Suraj, Jai Suraj. And I think Professor Madhukumar is also with us. And the presentation was extensive and very elaborated. And Professor Madhukumar also started from the basic level. So it has been a very informative session. I would request our session coordinator, Pratyusha Madam. She will raise the questions. There are a few questions in the chat box. Okay. Madam?
Thank you, madam. Thank you, madam. Thank you, sir, for your valuable session. It is very informative. Now, there are some questions regarding this topic from our audience. So, I read out this. First one question: what is the future perspectives of IoT in Indian commercial sector based on the research work which is going on?
Regarding regarding the opportunities provided in India, we know that agriculture is an important aspect in India. So as already mentioned by Madhukuma sir in his introductory slide, agriculture sector can be considered. A lot of applications in agriculture, including growth monitoring or weather, all these things can be done. And this is highly relevant scenario or in Indian scenario. And that in regarding social, I think all the energy technologies are already available. You have to just develop the application there or different applications. Most of the underlying protocols are there for developing basic hospital IoT technology. So these two can be considered as immediate hot area of research in IoT in India.
Thank you, sir. Another question is: what risk and challenges should be considered in the IoT?
Regarding real-time challenges, suppose you again consider the agriculture scenario. There is no guarantee that all the sensors or things will be placed in favorable climatic conditions. Sometimes it might be even be buried under the ground. So that is a real-time scenario. We can just simulate it anyway. But when it comes to the real-time scenario and all, there are different things to consider. Underground networks we have to consider, underwater networks we have to consider. All these are, when coming to real world, all these are significant challenges. And then, of course, mobility is a real challenge because that is actually the more nearby challenge. These are the mobility challenges are currently being addressed by researchers because, for example, consider an ambulance as provided by Madhukuma sir in his introductory slide. The ambulance has to communicate with the street light. The street light is actually a static Internet of Things device, but ambulance is always moving. So a moving entity has to intermittently connect. That is a real challenge. Mobility, I would say mobility is a real currently the most important real challenge.
One more question, sir. What is the impact of social IoT in user privacy?
Excuse me?
What is the impact of social IoT in users' privacy?
Okay. Regarding that, not just social Internet of Things, be it any application in Internet of Things, privacy is required. Because Internet of Things, as per its definition itself, it uses a lot of private information of the users. And when our private information gets passed on to a public domain as Internet, not just in social Internet of Things, in any case, it is highly essential that security should be maintained. So I would say that the impact of social IoT in users' privacy is the same as that of the privacy issues in any other IoT application, because IoT application requires the user data to go to the public domain. That is why I think edge computing and fog computing are often presented as alternatives to cloud computing technologies in IoT, because fog computing does not require all the data to always go to the cloud. If some part of the data, if the system feels that a particular data is more vulnerable, they can decide to get analyzed in the local research centers itself instead of going to the public cloud. So such kind of fog as well as edge technology, I think, can provide assistance in ensuring security of users, not just in social IoT but in any IoT application.
Thank you, sir. Now I would like to request Madam, please take over the session.
Thank you, Pratusha madam. And sir, I do not have the picture of Jay Suraj, so I could not prepare a digital certificate. But yes, I would request you to send me the picture. But yes, we have prepared a digital certificate which will be sending you in the mail also. So I'm just sharing the screen of the glimpse of it. So as a token of appreciation from our end, I'm just sharing. Kindly please wait before I share it so that you can have a glimpse of it. Yes. Is it visible, sir?
Yeah, it is coming. Uh, yes.
Okay, sir?
Yeah, I have seen. Yeah. Thank you.
Okay, sir. Okay. And sir, we'll be sending this in your mail. And I need the photograph of Jay Suraj, who was equally competent in today's lecture session.
Yeah,
And
I
I
will.
would send him the certificate by mail. And sir, we are thankful to you for sharing your precious time with us. And I would definitely look forward in having with you in our future programs as well. So
Thank
thank you,
you.
sir.
Thank you, ma'am. Yeah, thank you, ma'am. Hope the session was useful to everyone.
Yes,
And
sir. Yes, sir.
yeah, so I will send Jay Suraj's photo to you
Yes, sir.
to your email ID. Okay. Yeah.
Okay. Thank you, sir.
Wishing the very best for all the participants and for the FDP.
Thank you, sir. So I also thank all the participants for being with us. We will meet again tomorrow. Some other experts are there. So goodbye to Professor Madhu and Sri Jay Suraj for today. Goodbye to all the participants and thank you to all sir and madam and the entire department for being with us. So goodbye.
Thank you. Goodbye.
So I'm closing the session. Goodbye to all the participants. We'll meet again tomorrow sharp at 10 a.m.
Thank you, madam.